So what this school is about, what is the art, what are the techniques to simulate the early universe. So let me start by telling you what the early universe is. And by this, we simply mean the very first second of the universe. Understanding by this that this second is split in 3 different stages: inflation, a period of accelerated expansion; reheating, which is the following period of particle production, where the energy responsible for inflation gets converted into particles, and eventually these particles interact and thermalize, and they give rise to the third period, which is the thermal epoch, matching with the standard view of the hot Big Bang theory. Good. Now, here I want to emphasize that we are literally talking about the very first second of the universe. Of course, we don't know whether the universe really has a beginning or not, but certainly given the paradigm we have, in principle, you know, if there is an initial condition for inflation, we are talking from that moment on, and then the first second. Now, the question is, can we really simulate this very first instance of the universe? And if so, if we can simulate this, how can we do it, and what can we learn? Good. Now, let's go back to our sketch of the early universe. Now, what are interesting phenomena that we could try to address to understand from this epoch? There is, first of all, maybe one of the most famous cases, quantum fluctuations produced during inflation. There is also the possibility, or the necessity, if you want, in these theories, to have very explosive particle production mechanisms, both during inflation and reheating. There is the possibility, in beyond the standard model theories, to have phase transitions, both during reheating on the thermal epoch. And there is also the circumstance in some of these phase transitions that we produce topological defects, or in particular, cosmic strings. Now, what is the common factor to all these phenomena? By the way, one comment: if you want to ask something during the lecture itself, you are very welcome. The way to go is you have to raise up your electronic hand. So don't unmute yourself directly, please. Simply raise your electronic hand. Good. What is the common factor? Well, there is a common factor among all these physics, and that is the fact that all these phenomena, at least in their interesting incarnations, these are nonlinear field dynamics. Good. So let's put this aspect in the center. So these phenomena, which might be different among themselves, no, from phase transition to particle production, to nonlinear production of curvature fluctuations, to the dynamics of cosmic defects, they have in common that they are field dynamics and actually nonlinear, and hence it's very difficult to deal with them. Furthermore, there is a bunch of phenomenological consequences of this phenomenon, of this phenomena: gravitational wave production, realization of baryogenesis, realization of magnetogenesis, primordial black hole formation, production, just to give you a few. And all of this, in order to do them properly, you also need to deal with these nonlinearities. And even if you go not to these consequences, but to non-canonical scenarios, such as non-minimal cases, non-minimal gravitational interactions, non-minimal kinetic theories, turbulent or thermalizations, or more complicated stuff than usual, essentially, you are always trapped in this circumstance. You have to deal with very difficult nonlinear dynamics. So let's emphasize it once again. This is the core of the problem, and this implies that we need numerical tools, numerical simulations. Whereas you need analytical understanding, of course, to have a first idea of this phenomena and to understand what is the essence. At the end of the day, if you want to make a full prediction of them, you are going to have to go into numerical simulations. And this is why we have created a code such as CosmoLattice. So our school has two aims. On the one hand, it certainly aim to provide a pedagogical introduction to lattice field theory techniques in general. So if you want to, the techniques you need, that once you adapt them to simulate the dynamics of interacting fields in an expanding background, then you can address a lot of interesting problems in the early universe. Now, at the same time, we are going to do this in the introduction to this basic theory by introducing you to our code directly, CosmoLattice. This is a public code which is precisely prepared to deal with Lattice simulations of early universe scenarios, which is already written for a bunch of scenarios, and you could use also to write it for other scenarios. So the idea is to teach you, so that you learn during this school, how to simulate basic examples of nonlinear scalar and gauge field theory dynamics in an expanding universe. Right, very good. So now let me give you a sketch of what's gonna be the schedule during the school. This is a 5-day school. We have not a packed program, but you know, intense to some extent, because we are gonna cover a lot of material, but at the same time, we've decided to put only 3 lectures per day, or 3 events. So typical scheme of one day, the first day including today, it's gonna be, well, 1 lecture, first lecture, second lecture, and then third lecture, no more. So essentially, each of the lectures are gonna be 1 hour and a half. Typically, we are gonna split these lectures into 40 minutes, then 5 minutes break, then another 40 minutes. And in between the first 2, we'll have a coffee, at least here in the schedule of Europe. And in between the second and the third one, we'll have lunch, at least here in Europe. The idea is that we don't end very late in Europe. It's gonna be like 3:30, and which I believe is like 10 p.m.-ish or so in China. All right, good. Now, today is heavy on theory, because the 3 you know, events, the 3 lectures are literally on theory. Tomorrow, we'll start also with practice. So you see the day, tomorrow, Tuesday, what we will do, instead of having a theoretical lecture early in the morning, in Europe, sorry, I'm referring to European schedule with this, we'll start with some practice with CosmoLattice. And then we'll have another 2 lectures. So let me give you a brief overview. So today we are gonna start very, very slow and very simple. What is a lattice is gonna be the first lecture. So essentially we are gonna try to warm up such that nobody is lost from the beginning. It's gonna be really basic, say undergrad level. Then we are gonna give a basic overview of inflation and slightly some details of post-inflationary dynamics. And then we will close the day with evolution algorithms, which are all pretty generic stuff, which maybe half of you already know. Now, tomorrow we'll have the first practice, as I said, but then we will start having the first interesting theoretical lecture, where we will introduce how to really discretize scalar fields in an expanding background. And then at the end of the day, the last lecture, we will introduce lattice gauge theories of the abelian flavor, which are the simplest ones. On the next day, on Wednesday, we will have another practice. We will start complicating the kind of dynamics we are going to simulate. And then we will introduce at the theoretical level gravitational wave creation and propagation, and also the most complicated topic, perhaps, which is non-abelian lattice gauge techniques. So you see, gradually we are going to go building up. So don't get confused if today you find it too simple. It's just a way of warming up and introducing ourselves in the topic. On the 4th day, we will play on the practical level with gravitational waves, and then we will discuss on the theoretical level some aspects, advanced aspects like parallelization or plotting of CosmoLattice, and we will have an application of CosmoLattice, an interesting application to non-minimal gravitational interactions. On the final day, we'll have our final practice. We could dedicate that practice to either questions or doubts, or we introduce an example of scalar gauge theories. And then the final theoretical lecture will be about axionic interactions, which I think is a major interest for many people nowadays. And we will conclude the school with an overview. So as I said, we are going to start from the very basic to more advanced stuff. If today is very basic, we apologize for that, but we want to get everybody on board. On the other hand, as I said, this is just a warming up. We will get into the real stuff soon enough, starting tomorrow. Good. Now, notice that in red here, I'm highlighting the lectures that represent the theoretical core of the school. And I actually can put in orange those that represent phenomenological aspects, whereas in red, here are the pure theoretical parts, the more, if you want, academic way of presenting things. And lecture 9 and 10, however, will be more like applications of specific examples. Now, in purple here, we highlight the fact that we have practices. Now, last year, we did the practices with a room full of people in person, and of course, that made it easier for us to interact with the students. This year, we are going to do it for the first time online. So we are going to ask for your patience because, you know, we've never handled practice on real time online like this. And we are going to do trial and error and see how it goes, how we can handle your doubts, your questions, your problems with the code, etc. Good. And finally, we'll conclude the school on the last day with an overview. Excellent. All together, this is the scheme of the school. You see, it's a complete school, I would say, complete set of lectures, but we try not to make it very packed. So 3 lectures a day, you have time to play either in your morning for China or India, or in your afternoon in Europe with the lessons taught. Good. Who is teaching, who is lecturing in this school? Well, it's a bunch of people nowadays that we are developing and using CosmoLattice. To begin with, me, Adrien Floriot, and Francisco Torrenti, also known as Paco. We are the original creators and developers of CosmoLattice, but nowadays there is a bunch of other people also contributing, and they are also going to be lecturing in this school. Well, the group of people lecturing here actually have all kinds of levels in academia. There are a couple of us that we are faculty. Actually, we should congratulate Toby as well, because although well, he cannot join right now because he's not in Europe right now. Well, he got a permanent position, a faculty position very recently. And then we count also on our side with senior postdocs, Adrien, Paco, and Ben. We also have a junior postdoc, Ken, and we have PhD students who are also senior PhD students because they are towards the end of the PhD. So altogether, people very prepared that have been using on CosmoLattice for a long while or even created it in first place. And as a matter of fact, to be honest, it's going to be mostly them who are going to be lecturing. I'm only going to be taking care myself of this introduction and the overview at the very end. Good. So today's lecture, today's program is these 3 lectures, purely theory, but we are going to complement, of course, this lecture with this intro that I'm currently giving you. I'm going to give the intro. Paco, Francisco is going to give the first 2 lectures, and the last lecture is going to be on the hands-on Adrien. Now, on this intro, well, I would say I've already motivated the school, motivated what's the idea, and giving you an overview of who are our speakers. But before I think we start with the real theory, which would be this first lecture, what is a lattice, I think it's still interesting that we anticipate an overview of what CosmoLattice can do for you. So if you know nothing about this kind of simulations, please understand that this is just giving you now a taste of what you are going to learn in the school. We don't pretend you to follow the details of what I'm gonna say. We pretend to motivate you, to motivate and you to understand what's going to be the power of the techniques you are going to learn. So overview of CosmoLattice, let me give it before we switch into the actual core lecture. Well, CosmoLattice is a code that we released in 2021. But we work on it for a number of years before. And we release it together with a very long theory review of the techniques we're going to lecture you about in this school, and with a code manual. Both of these documents are over 100 pages, which of course might look overwhelming, but at the same time, they are that long because we made, I think, an effort to make a pedagogical effort such that you could start from scratch and learn in full detail what is the theory behind and what are the ways to implement that theory in our code. So for knowing about the code, well, because you are inscribed in the school, probably you have already visited our website. We have this website, cosmolattice.net, so very easy. And essentially, let me give you now the flavor of what CosmoLattice code can do. So it's a code that by default, without you having to do any effort, it already simulates a scalar gauge field dynamics. And when we say gauge, we actually mean abelian U1 and non-abelian SU2 interactions. And this is formulated in the modern language of Lattice QCD, lattice gauge invariant techniques. Essentially something called links and plaquettes that we will see in the third day of the school. So on the fourth lecture tomorrow, the lecture after the practice, we will cover the theory of how to introduce scalar fields in an expanding background. Whereas in lecture 5, we will include abelian gauge interactions, and in lecture 7, non-abelian gauge interaction of the type SU2. Nowadays, since it's so relevant, of course, we have including gravitational waves in CosmoLattice, and this is going to be the core of lecture 6. Now, CosmoLattice is written in C++ with a modular structure that separates physics from technical details. So essentially, if you are like a hardcore theorist, don't want to know much about the technicalities of the computation, you can still do wonderful applications with CosmoLattice to the physics without really having to dwell with the insights of CosmoLattice. Whereas if you are a computer geek and you really like details of programming, well, you can go to the technical part and really learn how we did this structure, which there is a lot of thought behind. In the practice sessions, this is where you will get familiarized with all this structure, so we will see that on real time. Now, CosmoLattice is a code that is parallelized in multiple spatial dimensions. What this means is that you can launch simulations to massive clusters with literally thousands of cores, thousands of computers if you want, and it will work all in parallel. Whereas you will write the whole code or the whole, the whole application of for your physics always in serial, always in series, as close as possible to the continuum, as a matter of fact. And how the internal parallelization works will be the core, well, part of the content of lecture 8, just for you to understand a little bit this insight. And finally, CosmoLattice is a code, a platform that already comes with a family of algorithms. And this means that you choose them from a menu, and that's pretty much it. So it's pretty simple on your side as a user, and explaining how these algorithms operate is the core of lecture 3, and their application into expanding universe circumstances is the core of lectures 4 to 7. Good. For more details, please visit always our website where you have here this menu on the top, and you can have access to a lot of information from the theory review to the manual to updates to information related to the code. Now, finally, before we switch into the actual pedagogical lecture, let me give you an overview of what is the real capability as it comes by default of CosmoLattice, and that's the following. It can solve the dynamics of minimally normalized kinetic terms of scalar fields, real scalar fields, no matter how complicated the potential of interaction is. It can also dwell with abelian gauge sectors, which means charged scalars, complex type, where we have implemented a lattice version of gauge covariant derivatives and field strength. And it can deal with non-abelian SU2 gauge interactions with doublets, such as the Higgs of the standard model, with the corresponding gauge covariant derivative of non-abelian interactions and field strength of non-abelian interactions. And this can be done with arbitrary potentials, no matter how complicated they are. Good. And it does the dynamics of all these kind of matter fields, or it can dwell with the dynamics, it can deal with the dynamics of all these matter fields in an expanding background, which means either you source the expansion of the universe by the content of all these fields, this is what we call self-consistent expansion, or you simply plug in a power law expansion in the background and you let them evolve on top of that. You can either do one of those two options. Typically, we solve the equations of motion in a Hamiltonian scheme, which means, for instance, for the simplest case of a scalar singlet field, This is the Klein-Gordon equation that describes its dynamics. I have here the wave operator in expanding background and the interactions through the potential. You define typically a conjugate momentum, and then the equations split into flavors, the kick and the drift. The kick is the actual evolution due to forces, due to the potential here. It's the evolution of the conjugate momentum. The drift is the evolution of the field amplitude related to the conjugate momentum. Now, we are going to teach you in the school how to put these variables in a lattice, which essentially is a collection of points. There is a number of points per dimension. In each of the 3 dimensions, there is a physical length, and there is a time step of evolution. And all of this implies also that in Fourier, there is always like 2 boundaries, an infrared and a UV boundary, and your momentum has to be always within these boundaries. And finally, notice that in order to introduce gauge fields, not only scalar fields, we'll do it with special techniques known as lattice gauge invariant techniques, which amounts to introduce some objects in the lattice called links and plaquettes. We will see this in detail on Wednesday. Now, a computer doesn't know about units. So essentially, how to deal with field theory in a computer amounts to make dimensionless all your variables. Typically, you have to choose 3 constants here. So F star is a dimension full constant, like a dimension 1 constant in terms of energy. And it's going to be a normalization of your scalar field sector. Omega star is a normalization of your time variable and your spatial coordinates. And it's going to normalize as well your gauge field. For reason, again, it will become more obvious in the 3rd day of the lectures. And finally, alpha is a constant, convenient, that you can choose in certain circumstances to make a conformal redefinition of your time variable in such a clever way that you can work in units where the time scale of your problem becomes constant. So how to choose these constants a priori is not obvious, but with this example, hopefully I will give you a taste of this. So imagine you have a situation where you have a dominant scalar field in the universe, and this is oscillating, and it's decaying with an amplitude, and the oscillations are such that the period is changing in time. Well, this doesn't change the fact that there is a typical amplitude, even though it's damped with time. There is always a typical amplitude, which is the initial one, and there is a typical period, which is the initial one, even if the period is changing. Then a clever choice here is to take as F star the initial amplitude of your scalar field, assuming it dominates the energy budget, and as omega star the inverse of the initial period. And now if you make a clever choice of alpha, you will arrive into some time coordinates that will make constant your period, which is very convenient for numerics. So we will try to teach you how to make clever choices of this kind along the school. Once you do that choice of constants, then you have to write a dimensionless potential, just this fashion, okay? You just normalize your physical potential by this constant, and then you just compute first derivative and second derivatives, which you are gonna write in one file, in the model file of CosmoLattice. And then you are ready to go, because then there is one file with physical parameters where you write the strength of your coupling, the type of algorithm you want, etc. And then you press play and go, okay? Now, we monitor the dynamics of the fields by following how good the expansion of the universe is being respected. If you want, how good energy conservation is respected. How do we do that? We source the expansion of the universe with the second Friedman equation. This means to source the expansion of the universe, the acceleration of the universe, with all kinetic term from scalar gauge sectors. Okay, so this is time derivative of singlets and time gauge derivative of charge scalars, gradient terms, which are charge gradient for the charge scalars, and then kinetic and gradient for gauge fields pure, which means electric and magnetic fields. And now if we sort the expansion of the universe like that, at least for the self-consistent, we monitor the conservation of energy, of the goodness of the expansion of the universe, by seeing how good this equation is balanced at every moment. So how good the left-hand side is equal to the right-hand side. And this is a non-trivial check that you can do at every time in order to see how good your dynamics are going. We can plot at any time we want during simulations volume averages, like mean values of a field, or energy densities, mean values of energy densities, field spectra of various kinds, like the amplitude of the field or the occupation number or something else, and then two-dimensional and three-dimensional distributions. So So essentially, CosmoLattice is a powerful tool where once you give it some initial conditions and define the equations of motion, the physics you want to solve, then you just have to choose what are the details of your simulation, what is your time step, what is the number of points per dimension, what is the minimum length scale you want to resolve, what's the algorithm you want to choose to do your simulation, what are your physical parameters, coupling and masses, define what observables you want to output, and press play, and then you get it. So in principle, it's rather easy as a user to get, at least on the basic usage of CosmoLattice, to get the output and results with the code. But now CosmoLattice is much more, because you should think of it as a platform where you can write and implement new theories, new field theories. So if you have a new problem, the next level of CosmoLattice is to implement this new physical problem, and then again you choose your lattice characterization, your couplings, etc., and press play. So CosmoLattice, very important message, is a platform for field theories. At the end of the day, if you learn how to use it properly, you are going to be able to decide which problem you want to solve with CosmoLattice. A very basic use of CosmoLattice is simply as a black box for the problems we have already pre-programmed, which are the ones I was describing before: singlets, abelian Higgs, abelian gauge theories, and SU2 non-abelian gauge theories. In reality, CosmoLattice is really split in a subset of black boxes, and the best way to really see this is that some of those black boxes are going to turn white for you during the school, because you are going to learn how to use basic modules of CosmoLattice to do your runs. Others are gray in the sense that it's going to require a bit more of an effort on your side to go deeper inside, but once you do that, you'll be able to implement essentially almost any problem you want. And finally, there is a set of really black boxes, which are those that dwell with the actual technicalities that for the majority of you are going to be really hidden unless you really like the aspects of parallelization or technicalities on the computational level. Well, as I said, the white boxes is the basic level of a good user, with a good level that you are going to learn in this school. The gray boxes are an advanced level. And of course, in the school, we are going to direct you towards them, but then it's up to you, to your work after the school, to really master that level. And black boxes are typically mostly for people who are really into computational aspects. In CosmoLattice, as I said, ready to use global scalar theories, abelian gauge and non-abelian gauge of the type FU2, and this is going to be the core of the theory of the main lectures. But at the same time, we are working on the update of CosmoLattice 2.0, which we wanted to release this year, but at the end we are late in our idea, so we will release it next year. And essentially, those updates are gonna make feasible for you to do gravitational wave production from any field theory, axion-like dynamics, non-minimal gravitational interactions, cosmic defect and cosmic string networks in particular, etc. All of this is implemented, and in the particular case of gravitational waves, you can already do it because it's already released. Whereas in the other cases, we are going to present these topics just as topical lectures, as applications, but the code for them is still not out for you to use it. Good. With this, I think I'm finished with the introduction. The idea now is that we are going to start with the actual first theory lecture, where we are going to introduce the concepts of the lattice. It's going to be Paco, who is going to be in charge of this. But I'm guessing that, well, just to make it easy, we can take now a 5 minutes break before Paco starts with his lecture. And of course, if you have any questions, please feel free to ask. I'll be very happy to address them. Thank you, guys, and welcome to the school. it's a good timing to go. I'm gonna mute myself and I take control as host, okay? And you can go.
Okay. Okay, very good. Thank you very much, Danny, for your introduction. So today I have a very important task, which is to cover the first two lectures of the school. And they are going to be, as Danny has said, basic. So I will try to go slow, and please ask me any questions you might have, because I think we are well on time. So, oops, 1 second. Okay, so basically in this first lecture, I'm gonna focus on the lattice part of CosmoLattice. Okay, I'm gonna 1 second. Yeah, I'm gonna try to introduce some basic lattice concepts that we will use later for CosmoLattice. But in this first lecture, I will not focus on applications, and in particular, I will not focus on cosmological applications. So this will be very generic, and in principle, this technique can be used to study other scenarios of interest. Then in the second lecture, in the second lecture, I will focus on the Cosmo part of CosmoLattice. Okay? Basically, I will, as Danny has said, I will introduce the basics of inflationary dynamics. I will start introducing a bit of post-inflationary dynamics, and then I will talk a bit about I will connect a bit the model that we are gonna study later on. I will explain a bit how to implement this in CosmoLattice, but I will not focus a lot on lattice lattice techniques. So this lecture will be purely theoretical. And then starting with lecture 3, and especially lecture 4, we will start putting everything together. Okay? We will see how to use the lattice techniques that I presented in the first lecture, how to use them to simulate or to study physics problems, cosmological problems that I will have motivated in lecture. Very well. So yeah, so this is the table of contents of this first lecture. I will start with very basic definitions of what is a lattice. Then I will talk a bit about how to implement boundary conditions in the lattice. Then I will introduce the concept of reciprocal lattice. This is basically how to go from a lattice in position space to a lattice in momentum space and back. Then I will introduce the concept of lattice derivative, how to compute time derivatives or spatial derivatives in a lattice. And then I will talk, this is a bit more technical, but I will explain how to compute power spectrum in a discrete lattice. Okay,
Paco,
so let's start.
Paco, sorry, can I remind something to everybody?
Yes, of course.
Yes, you are all most welcome to ask questions on real time during the lectures, but the way to do it, as I was saying during the intro, is that you raise up your electronic hand, and then me as a moderator, I will somehow interact with the speaker and let them know that you have a question if you do. Okay, don't unmute yourself directly, because otherwise it can be a bit difficult to handle situations like that, okay? But you are welcome really to ask questions on real time, not only after the lectures.
Okay. Thank you. Okay, so let's start with the first part, which is introducing what is a lattice. Okay, so a lattice is basically a set of regular discrete coordinates. And we are going to illustrate this with the simplest possible example, which is a one-dimensional lattice. For example, this is a lattice of 8 points or 8 sides. I will use both words indistinctly during my presentation. And we will use the capital N to denote the number of points of the lattice per dimension. Okay, so in this case, we have N equals 8. So as you can see, the distance between two neighbor points is the same throughout the lattice. Okay? The distance between this point and this point is the same one as the distance from this point to this point. This is what we call the lattice spacing, and we will denote this as dx. And the important thing here is that with just these two parameters, capital N and dx, we completely parameterize our one-dimensional. We just need to fix these two parameters. We will use this small n, little n, to tag the coordinates of the different nodes of the lattice. So basically, the coordinates go from x1 to x8, and basically the coordinates can be written as x star, where the x star is the origin of coordinates, plus n times the lattice spacing, dx. And as I have said, little n goes from 1 to capital N. Very well. So now the question is, okay, I have a continuous function. It is called, which we are going to call capital F. And the question is, how can we choose these two parameters, capital N and the lattice spacing, such that we have in the lattice a good representation of this continuous function? That's the fundamental question when you want to do a lattice simulation of a certain system. Of course, the lattice only has access to the values of the function at the lattice coordinate. So it only has access to the values of the function at the star, at the red stars that I have plotted. So what we're going to do is to define a lattice function, f of n, where f of n is going to be a function that is only defined at the coordinates of the lattice, and n tags the lattice point in which you are. So in this case, we have the lattice function is described by the values that go from f1 to f8. And basically, this lattice function coincides with the continuous function at the lattice coordinates that I have there. So do we have here a good lattice representation of this function? Of course, we need a better way of quantifying this. I will talk about this later. But qualitatively, just from the picture, we could say that yes, because the function behaves smoothly within different lattice nodes or lattice types. So in principle, yeah, the lattice captures quite well the behavior of the function. But we could have in this case, for example, for this continuous function, we have a bad lattice representation because with these 8 points, we cannot see well how the function behaves at a small scale. So in this case, for example, we will need to either increase the number of points or reduce the lattice spacing. So this is a bad lattice representation. Let's go back to our original function. And how can we say, what is the best, how can we evaluate if this is a good lattice representation? Where what we do is to choose the lattice spacing such that the relative difference between the lattice, between the function values at two neighbor points, fn plus 1 minus fn, divided by the lattice spacing, this is equal approximately, or this approximates quite well, the value of the derivative of the continuous function between two sides. So, for example, in this case, if we have f7 and f8, if the relative difference between f8 and f7 divided by dx, this approximates the continuous, the value of the continuous derivative of the continuous function at the middle between the 2 points, we say that we have a good lattice representation, right? So basically, we will discuss about this later when we talk about lattice derivatives. But basically, this means that we can the Taylor expansion of the continuous function up to first order of the continuous function, it approximates the derivative, real derivative in this sequence. We can improve. So perhaps the lattice representation here is not so good. So we can perhaps reduce the lattice spacing, or we can increase the number of points, but we keep the length of the lattice constant. So what we are doing is reducing the lattice spacing. We double the number of points, we reduce by half the lattice spacing. So we have 16 points here. this is obviously a much better representation, but we have a price to pay, which is that we must store twice as many numbers. So this is the first trade-off we have. Like we can arbitrarily, in principle, we can arbitrarily improve the accuracy of our lattice representation, but we have a price to pay, which is that we need more memory. This is the first trade-off of many that we will deal with lattice simulation. This is okay. So we have covered a one-dimensional lattice. Then we are gonna generalize this to two dimensions, to a two-dimensional lattice. In this case, we have x1, coordinates x1, x2, and we have a lattice space. In principle, we could have a lattice spacing, different lattice spacings on the horizontal axis and on the vertical axis, right? We could have the x here and the y here. We are going to focus on problems that are isotropic, so there is no particular reason why we should resolve one direction better than another. At least I cannot think right now on any cosmological scenario that will require a better resolution of one direction than on the other. So what we are going to do is to fix the x in both directions to be the same. The lattice spacing in both directions to be the same. I'm sorry. I'm sorry. Okay, so the points in the two-dimensional lattice, we are gonna tag them with the integers n1 and n2. N1 is gonna go from 1 to capital N. In this case, is 6, and n2 also goes from 1 to capital N. Yeah, the coordinates, as I have just said, are tagged with these two numbers, n1 to n2, and both n's, little n's, go from 1 to capital N, and we have n squared entries. Okay, so we need much more memory in two dimensions than in one dimension. Similarly, we can have a lattice representation of a continuous function, capital F. And we are going to call this function a little f, as before, and this is going to be dependent on both integer numbers, n1 and n2, right? And important notation, we are going to use, we are going to call this vector of two components, n1 and n2. We are going to denote it as n, bold n. This will be the vector of components. And similarly to before, we have a good lattice spacing. If in both their directions, both the x and y directions, we have the relative difference between the value of the function at two neighbor points divided by the lattice spacing. This equals or approximates the value of the partial derivative of the continuous function in the direction we are considering when evaluated between these two neighbor points. This is just an obvious generalization of the one-dimensional criteria. Three-dimensional lattice, the same. We have three lattice spacings. In principle, we are going to set them to be the same. And we have three numbers, n1, n2, and n3, to identify all the points of the lattice. The three numbers go from 1 to capital N. We have n cubed entries. Demand on memory in 3 dimensions is much larger than in 2 dimensions or in 1 dimension. Hopefully, we don't need to go to more higher dimensions in principle. Then we can represent a lattice function in this three-dimensional lattice. Again, with this small f, which depends on the three numbers, n1, n2, and n3, we call capital N, bold N, to the vector, and we call bold N to the vector of these three components, n1, n2, n3. And again, we have a good lattice spacing if in any of the three directions, the partial derivative within two neighboring points evaluated between these 2 points equals the relative approximates, the relative difference between the function, the difference between the function at these 2 points divided by the lattice space. So again, a generalization of the same criteria. And of course, we can arbitrarily go to d dimension, where d is a number that is larger than 3. We don't know how to plot this in in more than 3 dimensions. This is a 4-dimensional lattice according to Interstellar, right? I didn't make up this joke, it was Dennis. I just copied it. And basically, we just have, again, now we have the numbers to identify the different points of the lattice. We have n to the power of the entries in the lattice, and the little n's go from 1 to n. Again, we have a lattice function, little f of n, where n is a vector that has as components the numbers that identify the lattice points. And then we have a lattice spacing again, with the same, just generalizing the same criterion as before, but for all the directions of the lattice. Okay, so this, do you have any question until here? Okay, if not, we can continue. Now let's deal with boundary conditions on the lattice, no? Because of course the lattice is finite in size, so we need to deal with these boundary conditions. What do we do in the boundaries? Okay, so in order to illustrate this, let me consider this lattice with 8 points. Okay. And then, and the question is how do we deal with these boundaries, right? Because, for example, if we want to compute, we will see it later, but if we want to compute spatial derivative of these boundaries, we need, in principle, like the expressions for these derivatives do depend on what happens on the neighbors, right? But these boundaries, this boundary on the left doesn't have a neighbor on the left, and this boundary on the right doesn't have a neighbor on the right. So there are different approaches to deal with these boundaries. One is to just fix the boundary condition, such that the values of the lattice function at the left and right boundaries, these are constant in time, and then we just evolve but the function on the inside the bulk of the lattice. So in this case, f1 and f8 will be constant in time, and only the points going from f2 to f7, then this will be the only ones that evolve with time. This could be an interesting approach for, in certain problems. For example, I could imagine just solving the heat equation in a metallic surface when you know, like you are solving, for example, for the temperature of the surface, and you know what's the temperature on the boundaries because you are fixing the temperature of those boundaries. But this could be interesting for this kind of problems. But in cosmology, well, this really makes I cannot think of for the cosmological scenarios that we are gonna simulate in this school. This really makes no sense because, of course, what's happening at n equal 1 is gonna be affected by what's going on at n equals 0, and what's going on at n equal n, capital N, is gonna be influenced by what's happening at n plus 1. But of course, we don't know what's happening in these two outside the lattice, right? We don't know what's going on at n equals 0 and n equal n plus 1. So a second approach, which is the approach that CosmoLattice follows, is just to define periodic boundary conditions. Okay, the 8 points of the lattice evolve with time, but we fix the value of the function at n equals 0, which is a point that does not belong to the lattice, it's something that we have added extra. We fix this to be equal to the value of the function at n equal 8, in this case. And similarly, we fix the value of n equal 9 to be the same as the value of the function at n equal 1, n equals 1. So we can, for example, if we want to compute the gradient, the spatial gradient at this point, we just can take the relative difference between this one and this point and divide by dx. So topologically, what we really do is to solve for the time evolution of the lattice function, not in a normal R cube space, but a real cube space, but really in a ring, right? When the boundary is here, and this ring is also really a torus, one-dimensional torus. what do we do in 2 dimensions? Right? It's a generalization of what we do in 1 dimension. We need information of what's going happening here. Just for example, in the horizontal direction, we need information about what's happening at n1 equals n capital N plus 1. And what we do is to, as before, we fix the values of the function at this slice to be equal to the values at n1 equals 1. And in the other direction, we have the same. We do the same. We need to know the values at this n2 equals n plus 1. I repeat again, these points do not belong to the lattice. But we need information about what's happening here just to compute the derivative. So what we do is the same. We just identify this, the value of the function at this point, to be the same as the ones at the slice n2 equals 1. This is our lattice. This is what the points that do not belong to the boundary. We call this the bulk of the lattice. We will use this word, I think, quite a lot. And then the points that do not belong to the bulk, they are the boundary. They belong to the boundary. And then these cells, these points that do not belong to the lattice, we call them ghost cells because they don't belong to the lattice. And we will use, so this will be an important concept when we introduce our parallelization. When we introduce parallelization techniques, I think on Thursday. Yeah. So yeah, topologically, like so we have a periodic lattice, okay, where the values of the function at n plus capital N E I, where I is the unit vector in any of the 3 directions, equals the value of the function at n, right? And topologically, this is a torus in 2 dimensions, right? Because we take a 2-dimensional surface and we stick together the horizontal boundaries of the surface and then the vertical, and then the other boundaries of the surface, right? So we have a torus, which is periodic in both directions. The same is we do the same in 3 dimensions, right? And what is topologically the space where we are solving in the lattice when we impose this periodic boundary condition. So it's a torus in 3 dimensions. We cannot represent it, but it's like taking a cube and basically identifying the opposite side of the cube. Okay, so in this case we would stick together this side and this side of the cube, this side and this side of the cube, and this side and this side of the cube, right? And yeah, the generalization to d dimension is the same. It's obvious. And then, of course, we cannot, as I have said before, we cannot represent a lattice in d dimension. So we'll just stick this figure here. And yeah, so with this, we have finished the second section of the talk. So you have any question, this would be a nice place to ask them. If not, we will move on to the next section.
Paco, they were asking in the chat, what is the advantage of using periodic boundary condition versus fixed boundary conditions, I guess?
Well, I don't think there is an issue of advantage. It's an issue of what makes physical sense, right? If what we're gonna do is just simulate the universe, and what we're gonna do is to extract a piece of the small piece of the universe and just simulate what's going on there, right? So we don't. It wouldn't make sense to fix the boundary conditions because we don't know what's going on in the boundary. The boundaries are evolving with time also. So so it wouldn't make sense in this context. The only thing that we could do is just to kind of, I mean, we need to evolve these boundaries with time. because they are evolving. So yeah, I don't think the approach of using fixed boundary conditions wouldn't apply here. I don't know if I have answered the question.
Yeah, I think a complementary view on this is that we want to mimic like the infinity of the universe, but we are forced to be in a finite volume. And the only way to do this is precisely to allow the boundaries to not exist, which is periodic boundary conditions. Because in the moment you connect the sides of the hypertorus, then there are no boundaries, essentially. Okay, so in a sense, you are mimicking the infinity of the universe, where the only thing that matters is the local gradients, the local information, and then you don't make any distinction about any boundaries in reality, because there are no sub-boundaries in the real problems of the universe.
If there is another question.
Enrico, please, Enrico, unmute yourself, you can ask.
Yeah, I just wanted to ask, does that limit the time that you can evolve your field for? Like, if you wait enough time that that one side of your cube interacts with the other side of the cube, so basically it's interacting with itself in some sense, no? Does that still?
You mean if there is a boundary in the time direction? That
No. I'm saying if you evolve your field for long enough, at some point a signal starting from one side of the cube will reach the other side of the cube. And that side of the cube is not independent because it had the same initial conditions. So I was wondering whether this limits the total time you can actually evolve your field for.
Yeah, I mean, yeah, there is a limit, which is the. Let me try to answer your question. I've not done it just completely, but I think that yeah, there is for sure this limit the scales that we can solve. We can solve in the lattice. I mean, we have, for example, a wavelength that we are excited, for example, in the system, a wavelength a mode that has a wavelength which occupies the entire box. We cannot. Then that lattice doesn't work to solve the problem. Doesn't capture well the dynamics of the system. So it's not correct. We will need to increase the size of the lattice. So yeah, the periodic boundary conditions imply that you have that limitation. Imply that you cannot solve for if you have like a wavelength of the size of the length of the box, then this lattice wouldn't work.
But Paco, I have the feeling that the question is rather referring to what we could call the causal boundary, the fact that, of course, our fields are propagating at the speed of light, and after a number of time steps, eventually this represents a physical time in which signals have propagated and they touch each other because we have periodic boundary condition. Is this the question, Enrico?
Yeah, exactly. That was my question. Thank you.
Okay, so let me jump into it. So essentially, this depends on the problem, whether that's a problem or not. Okay, this depends really on the physical circumstance you are simulating. For typical cases like preheating, this is not very relevant. This we know from trial and error, that by increasing successively the lattice height, the length, all we do is, covering different length scales, but nothing is changing even if you go way beyond the causal distance in your box. But for other problems, we do stop the simulations when that happens. For instance, for a network of cosmological defects, because then they affect themselves, as you said, due to the actual finite volume, so yes, it's a concern in some cases, but not necessarily. Okay,
thank you.
Thank you, Danny. Okay, if there are no more questions, I think we can continue. And we are gonna.
Actually, there are, Paco, because in the chat there are, but I think let's pass them to the turn of questions, just not to dwell on the topic all the time, and you continue with your lecture.
Sorry, I cannot see if people are making questions.
No worries. I will control the chat, and I will let you know if there are new questions different than the same topic. However, the two questions right now, the new ones are related to the same aspect, so we address them at the end. Yeah.
Okay, very well, thank you. Okay, so let's continue. We are now gonna introduce the concept of Fourier lattice or reciprocal lattice. So first of all, just a comment: we are labeling the the coordinates that label the values of n that label the coordinate of the lattice. Okay, go from 1 to, in principle, we have made them to go from 1 to capital N. In reality, this is not really what we do in CosmoLattice, because CosmoLattice is written in C++, and the loops typically do not go from 1 to capital N, they really go from 0 to capital N minus 1. Okay, so this is just an important comment that we just need to take into account. And I think from now on, I will make Ni go from 0 to capital N minus 1. Okay, so this is the over lattice. Sorry, this is our lattice in position space, right? We have, as I have said, this lattice is parameterized by two parameters: delta of x, that is the spacing, which is dx, is the same, and then the number of points per dimension, and then the length of any of the sides of the cube is given by number of points multiplied by the lattice spacing and multiplied by dx. So basically, as I have said, no, with n and dx, we parameterize our lattice. Now let's introduce the concept of Fourier transform. We know how to define a Fourier transform in a continuum space. Here I'm going to introduce the Fourier transform in a lattice space. So this is a lattice function where n denotes the coordinate of the lattice in position space, and then we can write it as a Fourier transform where f of n, where n tilde here will denote the coordinate of the lattice after mean Fourier transform of the lattice in momentum space, and I will introduce this in a second, right? So this is the definition of the Fourier transform in the discrete, and this is the definition of the Fourier transform of the inverse Fourier transform. So if you want to go from position to momentum space, you use this Fourier transform. You want to go back from momentum space to position space, you use this. You use this expression, and you can show that one implies the other by just using this identity here. Right? I think. Okay. So yeah, as I have said, we have our real lattice or our lattice in position space, right? We have seen that we have that the position is discretized, and and it can be written in this way, where the numbers n1, n2, and n3 go from 0 to capital N minus 1, and then we have this periodicity condition such that that the value of the field at a given point, n, equals the value of the field at that point plus n times I, where I is the unit vector in any of the three directions of the lattice. So one can show that using this Fourier transform, we can obtain a Fourier lattice, which is the reciprocal of the real lattice, such that one can show that the fact that there is a discrete position in the real lattice implies that the Fourier transform mode or the Fourier transform function has an equivalent periodic condition, and then that the periodicity condition in the real lattice implies that the momentum, right, we are going to call this the momentum, is discretized. In other words, in this Fourier lattice, we are going n tilde identifies the points, identifies the coordinates of the different points of this lattice, this Fourier lattice, and we have three numbers. Again, we have n tilde 1, n tilde 2, and n tilde 3. And these three numbers are going to go from minus capital N to plus 1 to capital N over 2 in the steps of 1. No? In other words, if we have a three-dimensional lattice with 8 points, N1, N2, and N3 will go from -3 to 4. So in the Fourier lattice, the coordinates of the so the momenta that this lattice capture can be both positive and negative. This is unlike in position space. Then the physical momenta that are captured by the Fourier lattice is basically the momenta vector n tilde multiplied by 2 pi over L. We can see this if one takes the expression for the Fourier transform in the discrete and compares it with the one in the continuum. Okay? So basically, yeah, the physical momenta as the not physical momenta can be has like 3 components, K1, K2, and K3, and these components go from negative values to positive values. Let me just drink a bit of water. Okay, so this is I have taken a slice, a two-dimensional slice of a three-dimensional lattice in Fourier lattice. So this is the slice that corresponds to n n3 tilde equals 0, right? And I have said n1, n tilde 1 goes from -n over 2 plus 1 to n over 2, and n2 tilde goes from n from -n over 2 plus 1 to n over 2. As I have said, any of the 3 components can take positive and negative values. K1 will take, so this is the origin of coordinates, and then K1 in this direction is positive, and the component K1 is negative in this direction. And the same happens for K2. K2, the component K2 is positive in this direction and negative in this direction. All right. So we can immediately see from here that there is an infrared, a minimum momentum that can be captured by the lattice. Okay? And we are going to call this the infrared momentum. And basically, the infrared momentum is the momentum interval between 2 neighbor points of the Fourier lattice. Okay? In this case, it's going to be 2 pi over L. Okay? This is very important because this sets up, as I have said, the minimum momentum that you are going to cover correctly in the lattice. Smaller values of k, which correspond to larger scales in position space, will not be properly captured by this lattice. Will not be captured at all. Then, with this definition of the infrared momentum, we can write what we're going to call the linear momentum. This notation will be clear in just a couple of in 5 minutes. But basically, this momentum, which is here, can be written as KIR, which is 2 pi over L, multiplied by the n tilde. So basically, all the linear momenta is always a multiple. So not necessarily, but any of the 3 components of the linear momenta, of the linear momentum, is a multiple of the infrared momentum. Then we are also gonna define the Enquist momentum. I don't know if this is pronounced correctly. I think it's Enquist. This is the Enquist momentum, which is basically the momentum that corresponds to the interval between the center of coordinates and one of the lengths, one of the sides of the box. In this case, it's n over 2, the infrared momentum, which can be also written as pi over dx if we substitute the 2 pi over L in this expression. And then, so we have defined the infrared momentum, or the minimum momentum. And then the natural question is, what is the maximum momentum captured by the lattice? So this corresponds to the diagonal momentum that goes from the center of coordinates to one of the vertices of the cube. Okay? We are going to call this the ultraviolet momentum. And in a lattice of d dimension, is gonna be by pure geometry a square root of d n over 2 the infrared momentum. And so basically in a three-dimensional lattice, which is the case that we are gonna mostly consider, the infrared momentum is there is an infrared momentum, which is 2 pi over L, and a maximum or ultraviolet momentum, which is this infrared momentum multiplied by this factor. And that, just let me emphasize here that the Fourier lattice that I'm plotting here and the real lattice are reciprocal of each other. So you can go from one to the other and back again, right? And setting these two parameters in the real lattice, dx and capital M, which I have emphasized several times that parameterize the entire lattice, setting these numbers set also automatically the infrared momentum and the ultraviolet momentum. So we can either fix, so in fact, from a physics point of view, typically we have much better control of the infrared and the ultraviolet momentum than we want in our lattice, because typically we know which scale we are going to excite, or we are going to excite in the simulation. So just setting IR and UV, we can set N, the necessary N and dx. Okay, so is there any question until here, or do I continue? Okay, so yeah, if there are no questions, I'm going to continue with the topic of lattice derivative. Let me just check something, sorry. Oh, sorry. Sorry, I mean, yeah. For some reason, I go out of Keynote. Each time I press a key. Very well. So now we have talked about the lattice. Now we are going to introduce the time evolution of the function. Let me just try to get rid of this bar. Yeah. So we have already introduced the lattice. Now we need to introduce the time evolution of the function in the lattice, because this is what we are going to do in our simulation. So, for example, we can have a time that we are going to call T1, at which the lattice function has a given distribution, like this one. And then we are going to evolve the system until to a later time, which we are going to call T2. And the important thing here is that the difference between T2 and T1 is going to always be finite, and this interval between times is going to be set up by the time step, right? Which we are going to call dt. So we need also to fix dt when we want to evolve. We want to solve for the dynamics of some function in the lattice. And at T2, of course, the function will have a different distribution, which will be set up according to the equations of motion that we are going to solve. Now let me introduce new notation. I think we're going to focus on three-dimensional lattices from now on. So I'm going to introduce this vector of 4 components. It's going to be an italic, n in italic font, where the first component is going to give you the time step in which you are in the evolution, and the other 3 components are going to be the vector n identifying the position in which you are in the lattice, right? So as I have said, n1, n2, and n3 will go from 0 to capital N minus 1, and then n0 will go from 1 to 3 until the number of time steps we will have in our evolution. So how do we define derivatives in the lattice? Well, there are several ways, no? And the key challenge here is that, of course, we don't have access to we only have access to the values of the function in the lattice point, right? So there are different ways of defining derivatives, with some of them have advantages that the others do not have. And I'm going to introduce two definitions. And when I talk about lattice derivatives, I'm talking about both time derivatives and spatial derivatives. The first definition I'm going to introduce is the neutral derivative, which we are going to identify with this zero superindex here. And basically, if you want, the idea is that you want to compute the value of the derivative at a lattice at a given lattice point n. We just compute the absolute difference. As before, I was taking relative difference, I was introducing the derivatives before. It's really the absolute difference within the values of the function at n plus mu and n minus mu, where mu is the unit vector in any of the four directions of the lattice, or in any of the directions of the lattice, or time, the time direction. And this divided by 2 times either the time step or the lattice spacing, it gives you an approximation to the derivative of the function at n, at the point n. So for example, if you want to compute the derivatives at n equals 3, we just compute f4 minus f2 and divide by 2 times the space, the distance between the points. One can show by doing a Taylor expansion of these two terms that this recovers the value of the continuous function at f3 up to second order. So the difference between the real derivative and the lattice neutral derivative is going to be of order dt or dx squared. So as we move, basically, this means that as we reduce dx or dt, as we reduce these two parameters, the error will will reduce as a quadratic function. Yeah, and then a second definition of derivatives I want to introduce is the one of tart derivatives. A tart derivative has an advantage that it only uses one neighbor point. Okay, so for example, we can have so there are two kinds of tart derivatives. The first one is the forward derivative, which we're going to denote with a plus sign here, which is basically f the value of the function at n plus mu minus the value of the function at the point that you are computing the derivative. And similarly, there is the backward derivative that we're going to denote with a minus sign here. And it's basically f of n minus f of n minus mu. I think here this should be a plus minus sign, right?
Yes, that's a typo. Sorry about that.
Yeah, it's a typo. Yeah, this is a plus. This should be a plus minus. So for the backward derivative, this is fn minus mu. I will correct this in the slides that I upload in the. So yeah, so basically, you want to compute the tart derivative of f3. We can just compute the forward one as f4 minus f3 divided by dx or dt, and then if we want the backward derivative, we can use compute f3 minus f2, right? Okay, so let me bring some water first. So this has an issue, and it is that if we identify the point in which we are computing the derivative as a lattice point, so for example, if we identify the derivative at f3 as f4 minus f3 divided by dx, the problem that we have is that when we compute how good the approximation is, we see that unlike the neutral derivative, the error is not quadratic, but is linear. So really, it seems like this tart derivative is false. The key point here is that this derivative, this tart derivative, does not really approximate the value of the continuous derivative at f3, but at the intermediate point, it will be 3.5. Right? So basically, we can show that if we identify the point at which we compute the tart derivative at the lattice side, in this case 3, the difference is linear, the error is linear, because it's a linear function. But if we compute the tart derivative at the intermediate point 3.5, for example, the error is quadratic. So this is an important point, right? This is an important point to take into account. So if we use a tart derivative, we must take into account that we are obtaining when we do this operation is the value of the derivative of the continuous function at the intermediate point with the neighbor points. Hopefully, I have been able to explain this because it's a bit confusing to explain.
Paco, sorry, one observation is we are now entering a coffee break time. So it's up to you if you want to finish, this point of lattice derivative within the next 5 minutes, and then we resume with this lecture after the coffee break, or you want to stop right ahead, whatever you prefer.
I think I'm gonna do the next slide, and then we stop for the coffee break because it's a natural time to stop.
Good. Thank you.
Yeah. So we have introduced the neutral derivative, the charge derivative. Then we can in general write an arbitrary derivative, which we're gonna call without like this. We can write it as a linear combination. A generic derivative, we can always write it as a linear combination of the values of the function at different spatial points of the lattice, right? M goes over the entire lattice, right? In principle, it could be. And then the different points are weighted by this function, which is called Ti of LF. Okay? Ti is the weight, basically it's a linear is the weight of that the derivative gives to all points, to a given point of the lattice in the computation of this derivative. And it depends on both L, which is the point at which we are computing the derivative, and then M, which, as I have said, goes over the entire lattice. Okay, so by applying all the reasonable derivatives that we are gonna use will be variant under translation, which means that we can write this function here as a function of the relative difference with L minus M. So it only really depends on one parameter, on one index instead of two. And just by doing this, we are gonna call M star. We are gonna call this L minus M operation as M star. And then in general, we can always write an arbitrary derivative in this way. So we compare this generic definition with the definitions for the neutral and the charge derivative. You can obtain that the weights for the neutral derivatives are given by this function here. It depends on the Kronecker delta, on Kronecker deltas. And then the third one, depending on if we are evaluating the derivative at lattice size or at half lattice size plus half lattice spacing, then we have this expression for the weight. So just to conclude before the break, the goodness of the lattice presentation of continuous field is going to depend, or it's going to be controlled by three factors. One, of course, the smallness of the time spacing, or the time step, or the lattice spacing. Then which operator are we using for the lattice derivatives? And then the location where this lattice derivative operator is. And I think we can stop here for the coffee and continue in 5 minutes. Okay, so
okay.
Yeah,
thank you very much, Paco. So we take like 20 minutes break, I think, because we are a bit behind schedule.
Okay.
So the idea is we reconvene at 11 a.m. in Europe, 4:30 in India.
Okay.
Sorry, 2:30 in the afternoon in India, and 5 in China. I hope I got right the timings. Yeah, please correct me otherwise, okay? Yeah, but the idea is to take 20 minutes now. Well, Paco, then the stage is yours, whenever you want.
Very well, thank you, Danny. Okay, so what we have done before the break is just to write an arbitrary lattice spacing, arbitrary lattice derivative as a function of this weight here. All right. So now I'm gonna introduce the concept of lattice momentum, and a particular choice of lattice derivative will always have an associated lattice momentum. And what is it? Well, let's in order to introduce this momentum, let me introduce the lattice derivative I have just introduced, and then what we're going to do is to do a Fourier transform of this derivative, all right? Using the expression that for the Fourier transform that we introduced before. And then we can write this Fourier transformation in this way, and then using the shift property that I have just mentioned, we call n prima to n minus m, and then we can write this derivative in the following way, in this way, right? Where there is this summatory, there is a product of two summatories. This is the summatory over m of the index m over the entire lattice, and this is the second summatory over the entire lattice, which is given by this index and this label n prima. Okay, so this is precisely this second summatory is precisely the function, lattice function in momentum space, and then what we mimicking the equivalent expression in the continuum, this term here, we are going to call it we are going to identify it as minus I times the lattice momentum. Okay, so the lattice momentum is given by this expression, right? It's I times a summatory over the entire lattice of the weights multiplied by this exponential factor. And this is the lattice momentum because this mimics the equivalent situation in the continuum, right? When we take a partial derivative of a continuous function, then this drops the k factor in the exponential, and we have minus ik the function. Okay, so this is important. This lattice momentum is important because when there are situations in which we are gonna, for example, for Cage fields, we're gonna see that we are gonna set up the spectrum, the initial conditions, the spectrum of initial fluctuations in momentum space, where the momentum appears explicitly, the k appears explicitly, but then we are gonna go back to position space and evolve the fields in position space. So if in the position space we have discretized our scheme with a particular choice of lattice derivative, this means that when we go to momentum space, for coherence, we must choose the corresponding definition for the momentum, for the lattice momentum, right? And different weights, which define different discrete derivatives, will also give rise to different lattice momenta. So you can, I give it a leave this as an exercise, but you can show that the neutral derivative, sorry, the lattice momentum associated to the neutral derivative, sorry, is given by the sinus of 2 pi tilde n over n over capital N divided by dx. Okay, there's a sinus here. And then you can obtain equivalent expression for the charge derivative. Let me emphasize here that if you take the charge derivative and take it as the and take it such that what is this? And you are evaluating this charge derivative at the lattice side, at a given lattice side. This is a complex number. This is a complex number. So we can have lattice momenta that charge for certain. So we have lattice momenta that are complex for certain choices of the derivative. Let's in order to see how important can this be, let me show a comparison between the linear momentum, which we introduced before, which is this basically k. So basically this is the infrared momentum multiplied by the vector n tilde, and then compare it with, for example, with the charge the momentum associated to the charge derivative, which is given by this factor. Well, you can really see that for very low values of tilde n, this sinus is gonna recover the linear expression, but as we consider larger and larger values n tilde, of larger values of momenta, the approximation is not gonna be as good. So this is the figure that compares both momenta. In blue, you have the linear momenta. That's why it's linear. It's a linear function. And then in red, you have the chart momentum. And you can see what I was saying before. For low values of n tilde, they match, both functions match. But as you increase the value of n tilde, the value of the absolute, you increase the absolute value of the momenta, then of the momentum, the difference becomes larger and larger. Okay? This is for a particular lattice of 128 points. So at half the Enquist momentum, you have a difference of only 3%. At the Enquist momentum, you have a difference of 13%, and at square root of 2 times the, sorry, at 2 times the Enquist frequency, the Enquist momentum, we have a difference of 25%. And of course, the difference is maximum for the maximum value of the momentum. So this difference could be significant, and we must always take into account which momentum to choose, which definition of the momentum to choose. And finally, this is gonna be a bit more technical. I wanna introduce the discrete power spectrum. How to have the power spectrum of a certain function in the lattice. So we are going to deal with functions. So this is the continuum. Okay? This is a continuous function, right? And we are going to deal with functions that have fluctuations. At different space-time points, we are going to have functions with different amplitudes, right? Which means that one can compute the Fourier transform, and it's not going to be trivial. We will have a certain Fourier transform associated to the fluctuations of the function in position space. This is in the continuum. From here, we can compute the ensemble average of the function squared at a certain space-time point. And one can show, I'm going to put all the equations, one can show that this expression can be written as the integral of the differential of the logarithm of k multiplied by delta f, which is a function that depends on k and time, right? And this is the power spectrum. This is the power spectrum. And this power spectrum has the following expression. This is k cubed 2 pi squared, the power spectrum, a dimensionless power spectrum, not dimensionless, basically another power spectrum. It can be defined in both ways. To be honest, now I have the question. I don't know how to differentiate this power spectrum with this power spectrum. But basically, this is also a power spectrum, but with this k cube, without this k cube included. But the point is basically that you can relate this power spectrum with the two-point function, which is the average between the Fourier transformation fk, the product of Fourier transforms of fk, at two different k's, at k and k prima, right? So one can do this exercise and obtain this expression quite easily. Okay, so we know how to do this in the continuum, but the issue now is how to do this in the discrete, in the lattice. For this, well, let me first consider shells. Let me consider the lattice momentum space, the Fourier lattice, and extract a shell, a spherical shell, this three-dimensional lattice, which has as the minimum radius certain momentum k1, and then has as a maximum momentum k1 plus k infrared. This is a spherical shell, okay, and there are certain nodes, certain sides of the Fourier lattice that fall within this shell. Okay, so we extract this shell, right? We are gonna call this is we're gonna call this shell also a bin, and this bin basically corresponds to all momenta that are within k1 and k1 plus k infrared. We are going to call this bin, we are going to call it R1. From here, we can take the average momenta, the average momentum in this shell as K1 bar. So we're going to define it as K1 bar, and it's K infrared multiplied by N1. N1 is the momentum of the associated to the shell. And then we can count how many nodes are inside this shell. This is called the multiplicity. And in principle, one can this. I'm going to talk about this a bit later in more detail now. But there is a one can approximate this as being given by n1 t minus 1. So the momentum associated to the cell multiplied to the power of d minus 1 with this number of dimensions, and then multiplied by the solid angle in the spatial dimensions. In 3 dimensions, this is 4 pi n1 squared. We are going to focus on 3 dimensions now. So this is 4 pi n1 squared. And this is in principle approximation of the number of nodes that fell within this lattice. But this approximation, it's not true. We are going to exactly to what we are going to see now. But I'm assuming for now this multiplicity, we can just take the angular average of the Fourier transform at a certain K1. We can take it as the average of fk squared at all points of the cell within the cell. It's just sum the values of fk at all points within the cell, and we divide by the multiplicity. Why do we need this? Well, we need this to define the power spectrum in the discrete. So this is what we have obtained in the continuum. Let's focus on the lattice. In the lattice, the equivalent of the ensemble average of f squared in the lattice is the volume average of f squared within the lattice over the lattice, right? The volume average of f squared over the lattice. This is like you sum over all nodes of the lattice. You sum f squared over all nodes of the lattice, and we divide by the number of points. One can Fourier transform this and write this as 1 over n to the 6. The value of the field, 1 over n to the 6, and then sum over the entire Fourier lattice of the value of f squared. I'm not going to do the entire details. I'm going to just show you the basics of this demonstration. And then we can do a radial angular decomposition, right? Such that this sum over the entire lattice will decompose it as a sum over the shell, over the different shells, which are given by different values of n tilde, of the absolute value of n tilde, and then for each shell we sum over all lattice sites within that shell. And then we are gonna take the multiplicity of each cell to be this approximated expression, which is 4 pi n tilde square. So basically, this allows us to write this sum over a given shell as the average over that of the f n tilde square in that cell divided by the multiplicity. And then it's useful to write this expression in terms of this differential of logarithm of k. Not differential, but then this is finite, but we define this function to be chi ir divided by the linear momentum, such that we write this expression in this way. So why do we do this? Because if we take now this expression and we go to the continuous limit, this function delta of logarithm of k recovers the logarithm of k. And just comparing this expression in the continuum and this expression in the discrete, there is a natural definition for the lattice power spectrum, okay, which is this term here. Okay? So basically, we have written the volume average of the function square as a sum over beams of the delta logarithm of k multiplied by the lattice power spectrum, which takes this one. Okay? And this is the definition that this is a definition that we can use in the lattice. However, this has a sum. We have assumed that the multiplicity of each cell is 4 pi n tilde squared. And this is not exactly true. That's what I'm saying. We are assuming that this term here is, this average here is 1 over 4 pi n tilde squared, the sum over the nodes of the cell, and we have assumed that the multiplicity is 4 pi n tilde squared. This is not true. This is not true. To see this, let's go to different. Let's examine what happens for different cells. One can show that for shells that have a very small radius, it doesn't work very well, right? Works okay, perhaps, but then as we increase the radius of the cell, it becomes better and better. And the best shell for which this approximation holds very well is the shell that corresponds to the increased moment. Right? This is excellent. But then what happens? What happens is that for even shells with even larger momentum, average momentum, yeah, the shells go outside the lattice, right? So then this approximation fails completely because this approximation assumes that we have lattice site here, but of course there are parts of the shell that do not include that are outside the lattice, so they don't include lattice type. Right? So basically, assuming multiplicity, the multiplicity is 4 pi n tilde squared, we have found this expression. But in reality, one can do the correct computation with the real multiplicity, where the real multiplicity now is this. How this? I don't know how to say this letter right now. But this this letter. And basically, yeah, you use the real multiplicity, okay, which depends on n tilde. Then we can obtain this second expression, which is correct for all shells. And one can show that for subs have increased frequency, as I was qualitatively showing before, this expression here recovers the first one that we have obtained. So for more information on this issue, I recommend that you read the technical note 1 on the different definitions of the power spectrum that CosmoLattice uses, and you can see all the technical notes in this link in the website. They are all uploaded on the CosmoLattice website. So this is just the last slide of my presentation. I just want to emphasize that CosmoLattice allows to choose the type of power spectrum that you want to choose. First, you can use the what we call type 1. The type 1 lattice power spectrum is the one that takes into account the real multiplicity, and in principle, it's more correct. But then you can also use type 2, the type 2 lattice power spectrum, which corresponds to the approximated power spectrum that we have obtained that is correct only for sub-increased modes. Okay? And this is the approximation that assumes that the multiplicity is 4 pi n tilde squared. The reason why we also allow for this power spectrum is because all their codes, the previous to CosmoLattice, I think they were using this formulation for the power spectrum. So this allows for better comparison with results from all their codes. CosmoLattice also allows to choose for the version that you are using. There is like basically you need to choose the type, and then for each type you have 3 versions. For example, if you choose which and the difference between versions is how we treat the momentum k of n tilde here. So, for example, for type 1, we have these three versions. If you choose version 1, you take k as the mean momentum, basically the average between k, the maximum momentum and minimum momentum of the shell divided by 2. Then in version 2, this k is approximated as a weighted mean momentum, and in the version 3, this k is included in the average of each shell. I'm going a bit fast, but this is explaining a lot of detail in the technical note. And finally, you can choose the verbosity, which is basically gives you how much output you want to print. The higher the verbosity, the larger the information that you have. So for verbosity 0, you only have the value of k and the value of the power spectrum. But for verbosity 1, you have the weighted mean momentum and power spectrum. And then for verbosity 2, you have all the possible information that you have on the power spectrum. That would mean includes, for example, the root mean square of the k, the minimum and maximum momentum within the shell, and other things. So basically, it provides all the information. Everything is explained in detail in the technical note. Okay, and with this, I finish the first lecture. And this is a summary of everything that we have covered. So I think, thank you very much. And I think we can perhaps move to questions. And if not, I start with lecture 2.
I would say, Paco, that since we are a bit over time, because you're going to have roughly slightly over an hour for inflation,
very well.
Maybe we jump into inflation. And then if people have questions of everything at the end, together with inflation, we address them. Of course, later on, at the end of the day, of the last lecture of the day, we can also address questions from previous lectures.
Very well. I'm going to bring some water first. Okay, very well. So now we move to lecture 2 of the school, in which I have explained before. I will not talk about the lattice very much, only a bit in the end. And I will focus on the physics that we are interested in solving with lattice simulations. This will constitute an introduction to inflation and the post-inflationary dynamics. Probably many of you already know a bit about inflation. So I will cover what basic stuff in that sense. But it could be useful for some of you who are not as experienced with cosmology, with inflationary cosmology. And then I will discuss a bit about post-inflationary dynamics. This could be more new to more of you. Okay, so this is the table of contents of my presentation. I will start by introducing the Friedman equation and inflation. Then, as I was saying, I will introduce nonlinear field dynamics of inflation in the context of a certain situation, of a certain scenario. It will be preheating in a quartic potential. This will be the model that we will start, that we will simulate. We will start learning to simulate tomorrow. And then I will also talk a bit about how to implement this model with the program variables that CosmoLattice uses. This will be as a just to connect this lecture. This is what we will do tomorrow in more detail. Let's start with the let's start with the most basic equation you can have in physics, which is the most important equation, which is the Einstein equations of general relativity, right? These Einstein equations basically relate the geometry of the space with the matter content of the universe, right? Of the system. On the left-hand side, you have the geometrical part, which is described by the metric of the spacetime, mu nu. And then we can have the Ricci tensor and Ricci scalar associated with that metric. And we have also introduced lambda, which is a cosmological constant. This is the left-hand side. On the right-hand side, we have the expression tensor, which is the quantity that describes the content of our system. In this case, the universe as a whole. So, of course, solving these equations in general is extremely hard. What we are going to do is to apply the cosmological principle to this equation, which consists in stating the universe is homogeneous and isotropic at large scale. So one can show that only for the geometric part, one can show that the most generic metric that you can have in 4 dimensions that is homogeneous and isotropic is the Firma-Lemaitre-Robertson-Walker metric, which can be written in this way. It can be written as minus dt squared plus the metric of the three-dimensional special slices, which we write in this way, multiplied by a squared t of t, which is the scale factor. This is the here. No, we have like three different choices of k. It can have a k equal 1, k minus 1, or 0, and this gives you the spatial curvature. We can have positive spatial curvature, negative spatial curvature, or flat curvature. We will set k equals 0 in the next slide, so don't worry. This will be simplified. And also we define the Hubble parameter, h of t, as the rate of change of the scale factor. So basically, a dot, the derivative of a with respect to t, divided by the scale factor. Okay? This is not related with the Einstein equations. This is just working on the with the geometry of the space. Now, on the right-hand side, regarding matter, we can see that the expression tensor that is compatible with the cosmological principle takes the form of a perfect fluid, which can be written in this way. It depends on a function rho of t, which is the energy density, p of t, which is the pressure density of the fluid that we are going to include as a source of the Einstein of the general relativity equations, and then this mu of mu, the force velocity, which it must be correctly normalized, and for a moving observer, it's going to be just minus 1, 0, 0, 0. So putting this on the left-hand side, putting this on the right-hand side, we obtain the Feynman equations, which are 2 equations. We have the first Feynman equation and the second Feynman equation. In the first Feynman equations, the Hubble rate is sourced by the energy density of the associated to the fluid divided by 3 times Planck mass squared, and then terms related with cosmological constant and k. And then we have the second Feynman equation, which has also the combination of rho plus 3p plus this term that is related with the cosmological constant. There is a third equation, which is very important and is related with the conservation of the expression tensor. This is not an independent equation, and you can in fact derive this one by playing with the first and second Feynman equation. So there are only 2 independent equations. Really well. So we are gonna set now from now on k to 0 and lambda to 0, because this is the situation typically in the scenarios that we are gonna simulate. So let's introduce now the equation of a state, which is the ratio between the pressure and the energy density. And in principle, this is a function that depends on time, but we are going to set it as a constant, just to simplify. So if we consider this equation of a state to be constant, and we introduce this in the equations and we play a bit with them, you can show that you can solve the Feynman equations and show that if the equation of a state is -1, the scale factor expands exponentially as e to the ht, where h is a constant. And the scale factor, if the equation of state is larger than -1, it expands as a power law, as t, more specifically as t to the 2/3 1 plus omega, 1 plus w. So what is very important here, just in connection with what we are with inflation, is that if the equation of a state is larger than minus 1/3, the universe, so the scale factor, the second derivative of the scale factor is negative. So the universe is the expansion of the universe is decelerating. The opposite scenario is that if the equation of state is larger, so it's smaller than minus 1/3, the universe is accelerating. So yeah, so if equation of state is larger than minus 1/3, the universe decelerates, and this is the case for the standard model particles, which are described as radiation, which correspond to equation of state 1/3, or matter, which corresponds to equation of state 0. So the accelerating universe gives rise to the so-known problems of classical cosmology. The first one is the horizon problem. The horizon problem can be is best seen in the cosmic microwave background, right? When we see the cosmic microwave background, we see that the temperature is basically the same dependently on the direction of where we are looking. It's the temperature of the CMB is around 2.7 Kelvin, and then isotropies are of the order 10 to the minus 4. But this is a bit weird because if we assume a universe whose expansion is dominated by a fluid with equation of state larger than 1/3, which is, as I have said, the typical situation you just consider matter or radiation, then the CMB is formed by many causally disconnected regions. I think it's around the order of 10 to the 3 or 10 to the 4 causally disconnected regions. So there is no mechanism, in principle, that would explain why these regions have the same temperature. This is called the so-called horizon problem. And then the flatness problem is another problem, which basically is that right now we observe that the value of omega k, which is defined as minus k over A0 squared, H0 squared, these are the current values of the scale factor and the Hubble parameter. One can see that this parameter is very close to 0. It's one, in fact, I think it's compatible with exactly 0. But it's definitely much less than 1. But if we go to the external equations and we assume that the equation of state is larger than minus 1/3, then what we see is that this omega k equals 0 is a point of unstable equilibrium. In other words, if we go to the early universe and let the universe evolve, omega k will increase. The absolute value of omega k will increase very fast. So in order to explain the current value of omega k, right now we will need to have a very extreme fine-tuning in the early universe. Let's put omega k initially to be very, 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 very small. So these are the classical problems of classical cosmology, and we're not gonna explain. And then that's why the idea of inflation, the inflationary paradigm was initially introduced, right? Inflation basically consists in an early state of accelerated expansion of the universe, such that the second derivative of the scale factor is larger than 0. The universe accelerates, as I have said, and equivalently, the equation of state is less than minus 1/3. Right? So one can show shows this in a cosmology one can show this in a regular cosmology course, but one can show that the inflation solves the horizon and flatness problems. Basically, it explains why these regions of the CMB are causally connected, and why also for this case, omega k is equals 0 as a point of stable equilibrium. And so basically, inflation kind of solves these two problems, and also, more importantly, generates a primordial fluctuation that then allow for the later structure formation of the universe. So how can we sustain this accelerated expansion? Well, I think the simplest way of sustaining this expansion is just to consider a scalar field phi, okay? And we are gonna call this field the inflaton. Okay, so this is the inflaton, and the action of the inflaton, takes the following form, where here B of phi is the potential of the scalar field, the potential of the inflaton. And G here is the determinant of the metric. So we can compute the stress energy tensor associated with this action, right? In the usual form, you typically see this in a quantum field theory course, and one can show that the stress energy tensor takes this form, okay? Partial mu of phi, partial nu of phi, minus 1/2 of g mu nu, and the scalar product of the derivatives of phi. So then setting mu and nu to 0, we can get the energy density of the inflaton, and setting mu and nu to I, to one of the spatial coordinates, to the three spatial coordinates, and then doing the average, when we can compute the pressure of the inflaton. So the energy density, for example, it has a kinetic contribution that goes as phi dot squared, a gradient contribution that goes as the derivative, special derivative squared, and the potential energy. And then the pressure, you can see that the pressure is, so if we write this as kinetic plus gradient plus potential, the pressure is kinetic minus 1/3 of the gradient minus the potential. Then we can also, just minimizing the action with respect to the field, we can compute the scalar field equation of motion, which you should have probably seen, and which is sourced by the derivative of the potential with respect to the field, and then setting the energy density and pressure to these expressions in the Freeman equations, we can write the Freeman equation like this. So we have these three equations, and how we can use them to obtain an accelerated expansion. Then, well, let's go to the equation of a state. So the equation of a state is pressure divided by energy density. So it's kinetic, and we are gonna take the inflaton to be only time dependent. So we are gonna ignore the spatial fluctuations of the inflaton in this explanation, just for simplicity. So basically, the equation of a state is just kinetic minus potential divided kinetic plus potential. And then the issue is that we need the equation of a state to be smaller than minus 1/3. So how can we do this? Well, we just can consider a scenario in which the kinetic energy is much smaller than the potential energy. So basically, we can impose this condition that phi dot square is much less than the absolute value of the potential. If this holds, then the equation of a state is minus v per v, so it's -1, and we have an accelerated expansion. Moreover, we need a second. This is the first condition to sustain inflation. This is called the first slow roll condition. It's a slow roll because it's rolling. In this case, the field is slowly rolling towards the minimum. And then, but we also need a second condition, and it is that this state of inflation must take long enough such that the inflaton does not accelerate. Because if the inflaton accelerates, then this condition will be literally violated. This consists in basically setting the second derivative of the field to be much less than the other term. So much less than the friction term and much less than the derivative of the potential. So these two conditions can be allow us to define in a natural way the so-called slow roll parameters, which are called epsilon and eta. Epsilon is basically the kinetic energy divided by the potential energy with a certain numerical factor here, and eta is basically the acceleration of the field divided by the friction factor. And in order to have inflation, we need these two parameters to be much less than 1. When these parameters become of order 1, then inflation. And one can show that in the slow roll regime, when these conditions hold, we have that epsilon is approximately epsilon b, where epsilon b is this term that depends on the potential, and eta is approximately eta b minus epsilon b, and eta b is this potential. So basically, this allows us to just considering just a certain potential, we just, for example, m squared phi squared or lambda phi to the 4. We compute this expression with this potential and see for which values of the field amplitude we have that epsilon b is less than 1 and eta b is less than 1. And this will give us the field amplitudes for which the inflation takes place. And inflation ends, as I was saying, exactly when epsilon, which is approximately equal to epsilon b, is 1. Okay? This will give us the time when inflation ends.
Paco, sorry.
Yeah.
Just to make the observation. So you've been already speaking for 40 minutes since we started with the second lecture after the coffee break.
40, my God.
Yeah.
I'm very, very slow today.
So do you want to make the 5 minutes break now and then you have another 3/4 afterwards? Or
I think let me finish this and then we do the break.
Sure.
Thanks. Sorry, I thought I thought it was worse than mine. Okay, yeah. So as I have said, slow roll inflation generates an almost so as I have said before, right? Slow roll inflation generates an almost scale invariant spectrum of scalar and tensor perturbations. And also, I have said that the slow roll inflation generates a spectrum of fluctuations, right? So one can show that more specifically it generates an almost scale invariant spectrum of scalar and tensor perturbation. And it turns out that different potentials give rise to small differences in this spectra, which at first order can be parameterized by two numbers, the scalar tilt, Ns, and the tensor to scalar ratio. So I'm not going to go over the, I'm not going to explain in detail how this spectrum of fluctuations get generated and how they are parameterized. But what I want to emphasize here is that as different potentials predict different values for the scalar tilt and tensor to scalar ratio, we can just plot them in a figure of Ns versus R, and these quantities have been constrained by observations of the CMB. Right. So right now we have Ns, the experimental bounds on Ns are basically around 0.97, and there is a upper bound for the tensor to scalar ratio, which is of the order of 0.05. Right. So if we plot different potentials, we can see if the predictions for the potentials match the current constraints for these parameters or are experimentally ruled out. So the one I want to emphasize here is that monomial potentials are ruled out by observations of CMB anisotropy. For example, this is the prediction for the phi square potential, which is predicts a tensor to scalar ratio of 0.15 more or less, right? And this is much larger than the current upper bound for the tensor to scalar ratio. So this seems to point out that flat potentials are in principle favor observation with respect to monomial potential. I think we can do the break here, and then I will continue.
Thank you, Paco. If there is any quick question, we can take it. I'm happy to take it if Paco wants to take a break, of course.
I think I'm going to take a break. I come back in a couple of minutes.
Enjoy your freedom.
Thank you.
Okay, there is a question in the chat by Sajak. Let me read it out loud. What is the physical importance of power spectrum? Well, power spectrum is a very common, observable in cosmology because it characterizes the mean value of an observable function in an otherwise statistical distribution. So, for instance, the cosmic microwave background has anisotropies, and we typically represent these anisotropies by the angular power spectrum, which is the mean value per angle, of the typical amplitude of the anisotropies for that angular scale. And for us in field theory, in the lattice, the power spectrum is very relevant because it's the typical mean amplitude of the field square, of the field fluctuation square at a given momentum scale. So essentially, it gives you an idea of how power of a field is distributed in different wavelengths. And that's why it's relevant, because it's a way to understand how your physics are going on in Fourier space in terms of momenta. I hope that answers your question, but let me know otherwise. Antonino, you have a question?
Yes, maybe it's a basic question, but what is the physical meaning of the scalar tilt?
The scalar tilt, it simply has to do with the fact that the power spectrum expected in inflation in very, very basic scenarios, it's a power law at a given momentum scale, okay? And what does it mean, power law? It scales as k to some power, okay? So the amplitude of the power spectrum of the scalar fluctuations goes as k to some power. And this power on the exponent, this is the tilt, okay? And inflation predicts that it's quasi-scale invariant, but not quite. There's some red deviation, which is precisely this 0.97. So,
Okay.
So the meaning is that, inflation, at least in the basic scenarios that Paco is introducing, it's not exactly a scale invariant, it's slightly deviated, and measuring this deviation is important to support the idea of inflation and to differentiate among inflationary models.
Okay, thank you very much.
Okay, Paco, I guess we are ready and we can resume. So please.
Yeah. Give me 1 second, I share screen again. There we go. So you see my screen, right?
Yes, Paco, we see it. Yeah.
Right. So I think I'm better on time than I thought, because I forgot that I had finished lecture 1 later. So I think we are well on time. So okay, so I have just introduced very briefly the external equations and the inflationary paradigm. For more details, consult your cosmology textbook. But now I'm gonna talk a bit about nonlinear field dynamics after inflation, which is the typical physics that we wanna explore or wanna simulate with this simulation. And in particular, I will focus on the case of preheating, and preheating in particular with a quartic potential, which, as I have said, is what we want to simulate later. Okay, so let me just show diagram of the history of the universe. As I have said, and we have reasons to think that there was a stage of accelerated expansion of the universe, which is called inflation. And typically, when inflation dilutes any matter or that could have previously existed, so when inflation ends, which is defined as the time when h dot over h squared equals 1, then at this time, basically all the content, all the energy density of the universe is stored in the vacuum energy of the inflaton, provided by the inflaton. So we need a way of transferring energy from the inflaton to other fields. Right? This process is called reheating, and basically, the idea is precisely this: that we need to transfer energy from the inflaton to other fields, and eventually this must end up in this other field must thermalize, and eventually we must end with a thermal distribution of standard model particles. Right? This is called reheating, and one can show that, unlike in the previous inflationary state, during reheating, typically the scale factor evolves as a power law of T to the Q. The particular power law depends on the given model, on the given inflaton potential. And this thermalization must happen before the onset of feedback nucleosynthesis, which happens at 1 megaelectron volt. And then after reheating, the evolution of the universe must go as e to the 1/2 as the radiation domination to connect with the later evolution of the universe. And that's all. So the problem of so this reheating state is very interesting to study. I think that one of the main challenges is that the tales of reheating, and in particular, but also on the universe evolution of the universe, are very, very dependent on the particular high-energy physics models that one considers. Typically, it can involve nonlinear physics, which means that the equations of motion we must solve are nonlinear, non-perturbative, right? Which basically means that we cannot use the typical tools of Feynman diagrams to study parts of this physics, and then non-equilibrium physics, in other words, physics outside thermal equilibrium. So this is complicated. This can be complicated, and in particular, as Danny has commented before, and I'm going to emphasize now, in the early universe, we expect a lot of nonlinear phenomena. We can expect a growth of quantum fluctuations during inflation. We can have particle production during reheating or after inflation, but also during inflation in some scenarios. And we can also have phase transitions and cosmic effects. And this is precisely the kind of physics situations that we want to study with CosmoLattice. So for this presentation, I'm going to only focus on one, which is the production of particles after inflation, what we call preheating. Preheating. Preheating is a growth, is the existence of field instabilities due to non-perturbative effects, which cause an exponential growth of the field modes. So the particle number, which goes typically as the field mode square, is much larger than 1. This is a classical regime, and this justifies studying this system with classical lattice simulations. But in principle, let me emphasize here that lattice simulations can be used to study a plethora of scenarios, like from particle production during inflation, including like also preheating, production of gravitational waves, cosmic strings, other topological effects, phase transitions, oscillations, etc. But we're going to focus only on preheating at this stage. And as I said, I'm going to consider a quartic potential in particular for my example. But I have just said that monomial potentials are ruled out during inflation, right? Are ruled out to sustain inflation, right? However, even if this is true, there are many potentials that behave as a monomial around the minimum. One example is the alpha tractor T model. The alpha tractor T model is this potential which goes as a hyperbolic tangent to the P. Here, then you have lambda to the 4. Lambda is an energy scale, so lambda to the 4 gives you the potential energy at the plateau. P is a number. M here is for capital M is also a mass scale, so that what is inside the hyperbolic tangent is dimensionless. And P is a number that goes that can be larger than or equal than 2. We'll study scenarios in which it is larger than or equal than 2. So for example, this potential, we set P equal to here, we can see that, so we are depicting this potential in orange. For P equal 2, we can see that, yeah, it behaves as a pi squared potential around the minimum, but at larger inflaton amplitudes, behave as a plateau. So basically, as the potential is flatter, this makes it compatible with can make it compatible with inflationary constraints. I think I haven't written here explicitly, but I think it works. It works for values of capital M smaller than 5 times the planned mass. And in fact, if you take this value of capital M and move it to infinity, you can see that the dominant term, so basically this hyperbolic tangent for values of M going to infinity recovers the monomial potential. So this is an example of a model that justifies studying monomial potentials during preheating. We don't need to sustain we don't need this monomial potential to sustain slow roll inflation, just to be a good approximation to the complete potential after inflation. There is a second reason why I want to focus on monomial potential, and it is that the analytical treatment during initial linear regime is much easier than in other models. So it could be it's a nice start, to just learn a nice way of starting learning about preheating before jumping into more complicated models. Okay, so as I have said, I'm going to consider a quartic potential 1/4 lambda 5⁴. Lambda is the dimensionless coupling constant, and let me just solve the field and Riemann equation for a homogeneous field. Okay, so phi is only going to depend on time. This is valid during the initial stages of so during the immediately after inflation, but of course this will not be correct later on. But it's a good approximation during the first stages after inflation. So I have plotted here the evolution of the field amplitude. We have first a stage of slow roll inflation that goes until the value of the inflatons around 2 times the Planck mass, if I'm not wrong. And then at this time, inflation ends, and then it starts oscillating around the minimum of the potential. And this second stage of oscillation corresponds to preheating. So I have defined the time in which both regimes are separated as the time when the rate of change of the Hubble parameter is equal to 1. It's equal to -1. And I'm going to call this, very important, please remind this, I'm going to call phi star to the value of the inflaton amplitude at this time. Okay? So phi star is the value of the inflaton amplitude at the end of inflation. This is important because I will use this to define new variables later on. Okay, so I have also plotted here the solution for the scale factor. You can see that during the slow roll inflation, the scale factor expands exponentially. And then when inflation ends, the expansion slowens, and the equation of state, one can show that the equation of state, in fact, goes as 1/3. And this means that the scale factor goes as the square root of t. So yeah, in particular, one can obtain expressions for how the amplitude of these oscillations during the slow roll regime behave as a function of time. One can show that the amplitude of oscillations goes as t to the -1/2. So the amplitude of oscillation decreases with time, and also the frequency of the oscillation also changes with time. It decreases with t to the -1/2. I think these expressions were obtained by this important paper in the 1980s. And just to show you that we can obtain equivalent expressions for values, so for potentials that go as phi to the p, where p can be any number larger than or equal than 2. They are equivalent expressions. So one can show that for arbitrary monomial potentials that go as phi to the p, the inflaton oscillations can be the behavior of the inflaton oscillations can be approximately divided as factorized as decaying amplitude, A of phi, and an oscillatory function. The decaying amplitude goes as t to the minus 2 over p. So this recovers the result that I have shown for p equal 4, but this value for arbitrary values of p. And then you have the oscillations, which have a certain frequency that also depends on t. And in fact, the frequency of the oscillation decreases with time, except for the particular case p equal 2. For p equal 2, this is 0. So we have that the frequency of the oscillation is constant in time, in cosmic time, constant in cosmic time. Yeah. Similarly, you can see that the equation of a state generated by these oscillations can be written as p minus 2 over p plus 2. So this gives you 1/3 for a quartic potential and gives you 0 for a quadratic potential. So for a quadratic potential, the equation of a state is matter dominated. For quartic potential, the equation of a state is radiation dominated. And for the values of p, has other values. Very well. So now I have just introduced, I have just shown how the inflaton behaves, but now I want to preheat the universe. I want to transfer energy from the inflaton to other field. So as a toy model, we are gonna couple the inflaton to a massless daughter field, to a second field, which is gonna be massless, and we are gonna call this field the daughter field. Okay? And this is gonna be represented by the letter X. Someone is calling the telephone. So basically, you can substitute this potential in the field equation and the Feynman equation, and obtain these equations of motion. These are the equations of motion of the two fields, and this is the equation of motion of the Feynman of the scale factor. Okay? So these are the equations that we want to solve. Note that the field equations now incorporate this coupling of phi to the total field. Both equations incorporate this coupling to the other field. I haven't said that G is a dimensionless coupling constant, which we are going to set to be an arbitrary number for now. Okay, so this is the system of equations that we want to solve, and as initial condition, what we are going to do is to impose. So for phi, we have the initial homogeneous component, which is going to be the value at the end of the phi star. Remember the value of the inflaton amplitude at the end of inflation, and we are going to incorporate vacuum fluctuations, so some fluctuations over this homogeneous component. And we are going to do the same for the second field. The second field doesn't have a homogeneous component. It's going to, the average of this second field is going to be at 0, but we are going to add a small fluctuations as well to this second field. So yeah, we set the initial conditions at the end of inflation, and these fluctuations are going to be given by the usual expression for the power spectrum. The power spectrum is going to be here 1/2 times the frequency of the given mode. And the frequency of the mode depends on the effective mass of each of the two fields, which is given by the second derivative of the potential with respect to the field. So we can solve the equations, but it's useful not to solve them in these variables, in these space-time and field variables, but to define new variables, which we're going to call natural variables. So we have seen that the inflaton homogeneous mode goes like this. Like we have seen that the amplitude of the oscillations of the inflaton goes as t to the minus 1/2, so basically as the scale factor to the minus 1, and that the frequency of the oscillation also goes as t to the minus 1/2 to a to the minus 1, right? And we don't want, I mean, it's convenient in the lattice not to have a time-dependent frequency and a time-dependent amplitude, right? It's better if we find some sort of unit in which the amplitude is constant and the frequency is constant. So this is the idea behind the definition of natural variables, in which the amplitude and oscillation frequency are going to be constant. Just for concreteness, this omega star is the square root of lambda over phi star, which is the initial oscillation frequency. So when t equals t star. And t star, I think I haven't said that, but t star is the time at which inflation ends. So basically, all quantities that have a star mean that the quantity is being evaluated at the end of inflation. So what are the natural variables for a quartic potential? Well, we are going to define natural field amplitudes in this way, where we are multiplying the amplitude by a scale factor. This is a conformal scaling such that the amplitude does not decrease with time. And then we are going to also divide by phi star such that the numbers that we are going to deal with are of order 1. So this, we are going to call this field amplitudes curly phi chi. This is for the inflaton, this is for the rotor field. And yeah, and these are dimensionless variables. And then we are also going to define natural variables for time and space. For time in particular, we are going to use denote this natural time as u, and in this case, it's going to be consists just basically on a conformal scaling of time, such that this matrix is basically conformal time multiplied by omega star. Omega star is the initial oscillation frequency. So this way, no, this A minus 1 compensates the A minus 1 of the oscillation frequency. And then space are also going to be multiplied by omega star, such that u and the vector y are dimensionless. So we have natural time, which is u, natural space, which is y. So with this definition of variables, we can rewrite the field equations in the following way. This is the field equation for the inflaton. This is the field equation for the rotor field. And in both cases, there appears, primas here mean derivatives with respect to natural time. And we can see here that parameter, we have defined a very convenient parameter, which is called the resonance parameter, which is Q, and it's the ratio between G squared and lambda. And basically this gives you, see, this parameter depends on the interaction extent between both fields. And in principle, we can set it to any number if we want. So this is a number. And the dynamics of the fields are going to depend on which number we put there. One can show that these friction terms decrease as time to the minus 2, natural time to the minus 2. So we can just remove them just to simplify our analysis. And then what we're going to do is a linearized analysis. So what we are going to do is to take the fields and expand them up to linear order. So we ignore. So this will be valid in the initial stages after inflation, when the fluctuations are not very important, and they can be approximated by a linearized expansion. So we're going to show that at zeroth order, we have the zeroth order gives us the equation of motion of the homogeneous component of the inflaton. The homogeneous component of the zero order expansion terms are going to be denoted by a bar. Okay? So this gives you the zeroth order equation for the homogeneous component, and one can show that the solution. So this basically phi prima prima plus phi cube, which has as a solution elliptic cosinus, which can be approximated as a cosinus with a certain frequency. Okay, so basically this means that, as we have seen in natural time, the frequency of oscillations is constant, more or less constant. This is fine because this is the reason why we have introduced the concept of natural time, to have a frequency, oscillatory frequency, that is constant time. And then a linear order, we can just take the equation, linear order, we have the equation of motion of the fluctuations, which we are gonna transform to momentum space by doing a Fourier transformation. And we have the equations of motion for the fluctuation in for a given mode K, okay, for both the inflaton and the total field. So the inflaton, you can see both equations are kind of the equations of motion of harmonic oscillators with a time-dependent frequency, which we call omega star phi or omega star chi in both cases. And these are time-dependent because they have a time-dependent effective mass here. So the inflaton has a time-dependent effective mass that goes as 3 phi squared, where phi is the homogeneous oscillatory component of the inflaton. And the Lattice field has also this effective mass here, which in this case is Q pi bar squared. So you can see that as you change Q, you're gonna change the equation for the Lattice field fluctuation, but the equation for the inflaton fluctuations will not change. And then we have defined K tilde to be K over omega star. Right? So this is a dimensionless momentum. This is a dimensionless quantity. So one can show that when we are in this scenario and the effective frequency of the oscillators change in time non-adiabatically, so when the rate of change of this frequency is much larger than 1, then we have a process of parametric resonance, which means that the amplitude of this fluctuation square increase exponentially. Or more specifically, we can see that the evolution of omega of phi k squared goes as e to the 2 mu kt, okay? And the evolution of phi squared goes as e to the 2 mu kt, okay? Where mu and nu here are the so-called Floquet indices. Okay? Mu is the Floquet index of the inflaton, nu is the Floquet index of the dotted field. And one can show that, well, one can see that when the Floquet index is larger than 0, so when the real part of the Floquet index is larger than 0, then we have an resonant excitation. We have an exponential growth of the amplitude of this fluctuation. So, yeah, the fluctuations get excited through a process of parametric resonance after inflation. It's important here to take into account that the Floquet index of the inflaton does not depend on, that only depends on K, on the momentum, but the Floquet index of the dotted field depends both on K and on Q. Because, I mean, the equation of motion of the inflaton only depends on K, the equation of motion of the dotted field depends on both K and Q. So a really nice exercise now is to see how these Floquet indices depend on both K and Q to see for which momenta you have an exponential growth. Okay. So here I'm depicting the value of the Floquet index of the dotted field for different choices of Q, which is in the horizontal axis, and for different values of K in the vertical axis. So basically, the regions of the parameter space in which we have white, which are depicted in white, are those choices of K and Q, such that the real part of the Floquet index is 0. So for those choices, K and Q, we don't have an exponential growth. However, in the colored regions, what we have is we have the opposite situation. The real part of the Floquet index is larger than 0, so we have an exponential growth. And it goes from blue to red, from purple to red. So basically, the regions in which it's red have a stronger excitation. Okay, you can see here that the Floquet index ranges from 0 to 0.28 in this case. Yeah, so we can see typically we divide the parametric resonance regime, so the parametric resonance scenario, in two regimes. One which we call narrow resonance, which has Q less than 1, and a broad resonance where Q is larger or equal than 1. So for nanoresonance, the band, so for a certain value of Q, for example, let's say Q.1, then we have a very, very narrow band of momenta that are being excited. However, if we are in the resonance, for example, let's take Q18, we have a very wide band, right? That is being excited exponentially, right? So basically, in the broad resonance regime, the parametric resonance process is much stronger. The field fluctuations grow much faster. We can do the same exercise for the inflaton. What happens is for the inflaton, the equation of motion of the inflaton is the same one as the one for Dotter field, but for Q equals 3. So basically, we are in this scenario in which we have still a broad resonance, but the resonance is typically much weak. We're going to be typically much weaker if the Dotter field is broad resonance, right? Because we have a very narrow band here. Okay, so we can compute the variance of associated to the. So we can compute the variance of this. Of the field, right? By integrating the field modes as a function of the field modes squared in K, right? And yeah, this is what we see is that, for example, in this case, I have Ken. Ken, I thank Ken because he sent me this figure. What he did was to compute the evolution of the variance as a function of natural time for both the inflaton and the Dotter field. This is still in the linearized regime, just using as an input the Fouquet analysis. So we can see that this is an example for Q equals 500, and we can see that in this case the fluctuations of the Dotter field grow much faster than for the inflaton. Right? This is because, as I have seen in the previous diagram, the resonance of the Dotter field is much stronger than one for the inflaton. But of course, eventually, the variance of the fluctuation grows so much that the solution is not valid. In other words, non-linearities become relevant. So of course, what do we do in this case? We do lattice simulations. When we need lattice simulation to solve the complete equation of motion in 3+1 dimensions. So this connects with the last section of my talk, in which I will see how we could implement the first steps on how to implement this model in particular in CosmoLattice. I think this could be a nice time for questions. I think I've seen at least one. If not, I can continue. I think I have only 8 slides remaining. Whatever you prefer.
I would say, Paco, let's finish. So we finish on time in case some people need, lunch or dinner or whatever. And then we, of course, allow for time for questions afterwards in any case.
Very good. Great. So yeah, so we are going to discuss how program variables in CosmoLattice. This is the first step towards implementing this model in CosmoLattice, and this connects naturally with what we will do tomorrow in the practical session. So this is this overlaps a bit with what Danny has explained in the introduction. Okay? But this is very important. So this is the point when you need to ask questions if there is something that you don't have clear. Okay? This is very important. In the lattice, what we are going to do is to operate in a set of dimensionless space-time and field variables. Okay? This is going to call program variables. In practice, what we need for a given model, we need to choose 3 things to define these program variables. One is alpha, is a number, and then the other 2 parameters are f star and omega star, which have units of energy. Okay? So the CosmoLattice is going to solve for the field equation, not in the variables I have just shown, but these program variables, which are related with the old variables, let's say, in this way. So in particular, it operates in a time, which we are going to call denoted with a tilde, that includes omega star here, such that it is dimensionless, and it has this conformal factor a to the minus alpha. So if you set alpha equals 0, we have cosmic time up to a dimension full factor. If you set alpha equal 1, we have conformal time, but you can solve the equation in any alpha time that you want. Okay? We call this the alpha time. And then there is also we also operate in dimensionless space units, which consist in multiplying the space coordinates, spatial coordinates by omega star. And then all the fields will be rescaled also by this f star, which is a mass scale, which you can set arbitrarily in principle. So we will denote f dot two derivatives of the field with respect to cosmic time, and f prima two derivatives of the field with respect to program time, with respect to this program time. So so we will also work in other. We will also define in the lattice other dimensionless quantities or program as a function of other program variables for convenience. Right? And these quantities, these quantities, which are a function of program variables, will be denoted with diacritic field with this field. So, for example, the most important one is the program potential. In the program potential, it consists basically in writing the all potential as a function of the program field, program amplitudes of the field, divided by f star squared omega star. And how to choose the program variables? How to choose program variables chosen? So these are chosen by a case-by-case basis. There is an optimal choice for monomial potentials too. Okay? We are in a scenario in which we have one dominating field, which has a monomial potential, like the case we have just introduced. There is a natural choice of which is to choose alpha to 3 times p minus 2 or p plus 2, so that this is cosmic time. This gives you cosmic time for p equal 2 and conformal time for p equal 2. Okay? Then we can set f star to phi star, such that, where phi star is the amplitude of the inflation, and omega star is going to be we are going to set it up to the oscillation frequency at the end of inflation, whose expression I have is so in this variable, the oscillation frequency, this choice ensures that the oscillation frequency is approximately constant, and time and space scales are of order 1. Okay? So if we use this alpha time and solve for the scalar dynamics for this potential, we will see that the oscillation frequency is approximately constant. This is exactly the same that we have done before for the quartic potential, but this is for generic monomial potential. So, for example, let's consider an inflaton with a quartic potential coupled to a daughter field for quadratic interaction. Yeah? So, basically, let's consider the same potential that I have just, the same situation, the same scenario that I have just introduced. This is preheating with a quartic potential. So, this is the Lagrangian, and we have the potential here, which is the sum of 2 terms. The inflaton potential, lambda phi to the 4, and the interaction term that goes as phi squared chi squared. So we have 2 parameters here. The number of scalar singlets that we're going to add to the model, it's going to be 2. Have one for the inflaton, one for the one is the inflaton, one is the total field, and then we have 2 potential terms, okay? The inflaton potential and the interaction term. Okay? So we have NF equal to 2 scalar singlets, 2 potential terms, and T equals 2. These are variables that are written explicitly in the model file that we shall see tomorrow in more detail. And then, according to the previous prescription, we fix the program variables to this. We have alpha equal 1, we have f star equals phi star, dependent the amplitude of the inflaton at the end of inflation, and then omega star is set to be the initial oscillation frequency, so square root of lambda multiplied by phi star. So using this definition, this choice, we have the program variables that we're going to use to solve for this system in CosmoLattice are going to be phi star, which is phi over phi tilde, which is going to be phi over phi star, this alpha time, which is defined this way, and this natural space coordinate. So just a very important comment. This is not exactly the natural variables that I was introducing, or I was using in the previous section, because now this includes this does not include these variables. These program variables do not include a rescaling of the field amplitudes by the scale factor. Okay? So before we were using exactly the same variables, but we were also except that we were also including a conformal rescaling on the infloton. Okay? For CosmoLattice, we don't do that. In CosmoLattice, we use program variables that do not include a conformal rescaling of the infloton amplitude. Okay. So basically, yeah, we have the program potential, and we have the resonance parameter. Let me call this term B tilde. Sorry, let me say this again. From the potential, so from this potential here, we can compute the program potential this way, and one can show that this given by 1/4 phi tilde to the 4 plus 1/2 q phi tilde square, where q is the resonance parameter. I leave this to you as an exercise. And then we call the first term B tilde 0 and the second term B tilde 1. This is the program potential that we are going to introduce explicitly in CosmoLattice. We can also define a program energy density and program pressure density with an equivalent definition to the potential to the program potential. So we have that the energy density in program variables is kinetic plus gradient plus potential, and the pressure in the program pressure is kinetic minus 1/3 of the gradient minus potential, when the kinetic gradient and the kinetic and gradient contributions have contributions from the kinetic energies of all fields, which are written in this way in program units, and the potential is a sum over the potential terms of all, or is a sum over the potential terms. So in this case, with some this goes from 0 to the number of terms of the potential minus 1. And we can, from these are local quantities, but we can compute volume average quantities as the average over as the volume average of the kinetic gradient potential contributions, or as a volume average over the entire lattice of this quantity. Right? So basically, what CosmoLattice does, is to solve for these equations. Right? These are the equations of motion written in program variables. Right? This is one of the inflaton, this is the one of the inflaton, this is one of the daughter field, and solves also for the scale factor equation, the Feynman equation, in program variables. And just to emphasize this, what we really have is n cubed. We have 2 times n cubed equations for that we need to solve for each of the fields. We have n cubed because we have n points on the lattice. So this is solved locally at each point, and the factor 2 is because we are using the Hamiltonian scheme. So this is a second order equation that we decompose as 2 first order equations. But the scale factor is sourced by the volume averages of the energies, and this is just one equation. So the evolution of the scale factor takes nothing in time. The time-consuming operation is based to solve for the field equations. And the accuracy of the solution is monitored through the first Feynman equation. So we use the second Feynman equation to evolve the system, but the first one, the first one must be always obeyed at a certain degree of approximation if our simulation is gonna be correct of simulation is going to reproduce the dynamics in the continuum sufficiently well. And this is monitored through by measuring the relative difference between the left and right hand side of the first Feynman equation. So so basically, Adrian will show. So this afternoon, Adrian will show algorithms to solve differential equations in general, like the ones I'm showing. And then tomorrow at lecture 4, Jorge will explain how to apply the algorithms that Adrian will explain to solve specifically the equations of motion of interacting scalar fields. And of course, we will start playing with this in the practical session tomorrow. And just, I think this is my last slide. I just want to mention briefly what CosmoLattice does to impose initial condition. So in the continuum, right? In the continuum, we have a spectrum of initial fluctuations, right? That I have shown before, right? In the previous subsection. This is the same, but written in program variables. And then we need to deal with this in the lattice, right? in the lattice. So for that, we use the definition for the power spectrum in the lattice that I have introduced in the first step. And so let me just put everything together. So yeah, basically, the idea is that we need to match, right? We need to sorry, I'm a bit lost right now. Okay, yeah. Let me just rephrase again, right? We have seen that in the continuum, we have when we were solving the linearized equations, we were imposing this spectrum of fluctuations, right? Which goes as 1/2 I squared frequency, right? We can write this in program units. This is what we have done here. And then, of course, when we are working in the lattice, we need to use the power spectrum in the discrete, right? We need to use the definition of the power spectrum in the discrete. So what we do is to match this power spectrum to the in the discrete to the one in the continuum, so that this one recovers the one in the continuum in the continuum limit. All right. And yeah, in practice, what CosmoLattice does is to impose fluctuations in this node as a sum of left and right moving waves, such that the final result are Gaussian fluctuations. And the way in which this is done is just to have the fluctuations here. And what we do to sum two waves, one left moving wave and one right moving wave. And in order to ensure that the final result is Gaussian fluctuations, we impose these amplitudes to have a Rayleigh distribution, right? Whose expected root mean squared is given by this expression, and each wave also has two random phases. Right? And then the fluctuations of the time derivatives are imposed by differentiating this with respect to time. So basically, this construction ensures that initially we have Gaussian fluctuation in our simulation, and that they match the expected expression in the continuum. And with this, I think I'm going to finish. So thank you very much. I think we can move on now to questions.
Thank you, Paco. Okay, so I'm pretty much on time, almost, just 5 minutes past time. Very good. So well done. I see there is a question by Kursit. Please, you can unmute yourself.
So, can you go to the slide for where we have explained the resonance band?
Okay. Could you give me 1 second because I have problems with my earphones?
Can you hear me? No.
Yeah, I can hear you.
Oh, okay. So I'm saying, can you go to the slide where you have explained the resonance band diagram?
Sorry,
Band
what?
diagram.
What?
Band diagram. Where?
Ah, the diagram. You mean this one? Okay, yes. So which diagrams? I'm sorry, I haven't heard you well.
Yes, this diagram. Yes. So for this case, you can see that your frequency is always positive. Okay. So if your frequency is always positive, then how your mode is going exponentially then?
Sorry, I'm sorry, can you repeat the question? It's because I'm having
Yes.
problems
Yeah,
with my
I can
sound.
repeat you the question, Paco. The question is why, if the effective frequency square is positive, how is it possible to have exponential solutions?
Yes.
Okay, thank you very much. I'm sorry, I have problems with the sound system right now. So no, it's basically because we have time-dependent frequency. So it's true, for example, in this case, on this one, we have Q is a positive number, that's right. So in principle, this were constant. This will have this will be a constant mass, and this will kill the resonance for all values of K which are smaller than this. But this is time dependent. That's the key point. The key point is that as the inflaton is oscillating around the minimum of the potential, this is inducing a time-dependent effective mass, and this is inducing a resonant growth. Like if you have I don't know how to say this. A spring that you are pushing constant.
So for your exponential growth, you don't need any negative frequency.
No, no. In this system in particular, it's everything is phi squared and Q is always positive.
All is positive, yes. In this case.
Yes.
So how do you plot this this diagram, right hand diagram, this spectrum? What is the algorithm here?
Basically, what we do is what Ken Marshall did, because he is the one who did this diagram with my collaborator. It's precisely to solve for this equation, right?
Yes.
And extract the value of the exponent from the solution.
So sorry. How do we extract this exponential? Because this is the positive solution, frequency is positive, then how do we extract this negative solution? I'm saying exponential solution. So this is my concern actually.
No, but I think I think it's what we use to solve literally this equation of motion. So we plot the evolution of chi of k as a function of time, and we see that it's a log scale. It's just a straight line, and from there we extract exponent. So I don't understand your question. So
is the envelope that is growing exponentially. Okay, it's an oscillatory field that
Yes.
its envelope, its amplitude is growing exponentially. So they just measure the envelope of the oscillations, and that's the exponent.
sorry.
Okay.
And the reason.
Okay, thank you.
Look,
Yes,
this looks
yes.
like a oscillator-like equation. If you can put it back, sorry, Paco.
Yeah, sorry.
Yeah, but you see, positive defined effective frequencies doesn't mean that there are no instabilities. Because if you violate adiabaticity, this is not a harmonic oscillator. It's something else.
Yes.
And this is how you get these diagrams and these exponential instabilities. Violating
where the non-adaptivity is violating, we are taking this value of mu k.
Is the violation of adiabaticity at the bottom of the potential that defines these values of nu, given a coupling strength or a resonance parameter.
Okay, thank you.
Okay, next question. I think in the queue is Kursit. Oh no, that was the previous question. Can you remove your hand if that was the case? Okay, Devika, please go ahead.
Hello, can you hear me?
Yes.
Okay, so my first question is actually a bit general question. What would you say is the advantage of using this lattice framework for solving these equations rather than like a more the usual like Runge-Kutta algorithm or something like that?
Well, these are different things. We can use lattice. So we haven't talked about evolution algorithms yet. I think Adrian will introduce this afternoon. But this principle is two disconnected things. If you decide to do a lattice simulation, you can use any algorithm you want. So you can use, for example, a Runge-Kutta algorithm. And in fact, I think CosmoLattice, I don't know the public version, but for sure, in our private version, we have already implemented Runge-Kutta algorithms to solve for the field equations. So one thing is the choice of using lattice simulation versus linearized evolutions that are shown, and the other thing is which algorithm to use for the simulation. I don't know if I have answered your question.
No, so what I wanted to know is if I use a lattice simulation, what would be the, what advantage would I gain over the usual way of solving these equations numerically? Like, is it faster or is there something like that?
Well, I think it's more accurate. I mean, with respect versus, so using lattice simulation versus what? Versus solving the linearized equations. That's what you are asking.
Yes.
Oh, precisely because the linearized equations have a limitation. It's precisely this. There is a which you cannot trust the linearized approximation,
right?
Because then there's a point in which you have so much energy in the fluctuations that this is going to backreact onto the equations. So you need to solve for the complete full three-dimensional equations without any approximation. And this can only be done with lattice simulation.
Okay, I understand. Okay. And my second question is, maybe you discussed this and I missed it, but from where are you getting the gradient term towards the end of the slides? I think the second last slide probably. You had some gradient terms in the equation. Could you please explain where those came from?
Final part.
Towards the end where you are showing the equations. Yes, these.
Yeah. What is your question?
Yes. So the gradient contribution that you have. Yes, I probably didn't understand this properly. So towards the beginning, I think we said that phi depends only on time, so we don't have this term. So, and then is it as in where is this term arising from here? Is it like a more generalized way of writing this?
No, this is just the energy density within in program variables. There's nothing else. So so we have kinetic gradient as we have in usual variables. We can decompose the energy density as kinetic plus gradient plus potential. And if you take no, so this is this is just the gradient contribution to energy density between the units.
Okay, I understand. Sorry, this is just for the energy density. Okay, I was confused with something else. Okay, thank you.
Thank you. Sure, you can ask.
All right. Thank you for the talk. And so I would like to know, like, for that, how does one like change the initial fluctuation in the code? Like towards the end, you mentioned the setting the initial fluctuation.
Let me go back. So this is what CosmoLattice does by default. So you don't change anything.
Right.
The power spectrum will be set to this expression here in the continuum or its equivalent formulation in this field. But of course, you can always go to the function, to the particular file in the code that implements the equation, and you can change the function to something else. But there is a file in the code which is called fluctuation generator.h, I think. We can perhaps go over these questions perhaps more detail tomorrow or on Wednesday in the practical session. But yeah, I think you can, in principle, change that. But it's not easy. This is not a white box, as Danny was saying in the introduction. It's more a gray box. The change is not as easy as one would expect. But one can do that. One can change the initial situation.
Yeah, and let me add that not only you can change it by hand, as Paco is saying, although you need to understand a little bit now the structure of the code to do that. We have also worked out the possibility that you introduce an input file which has a numerically codified a spectrum from whatever other application you work out, and then the CosmoLattice will read that spectrum numerically, you know, and then it can have an arbitrary shape. But this is not in the public branch yet. Okay, hopefully we will release that in CosmoLattice 2.0 next year. So you can put arbitrary form spectrum.
Okay, yeah, thank you for the answer. Thank you.
Okay. Ahmadullah, please.
Hello, sir. Can you hear me?
Yes.
So how CosmoLattice takes care of the back reaction terms?
Well, just solving exactly the complete equation of motion. So CosmoLattice does solve these equations exactly, which take into account, which don't have an approximation. So, like, there is no, these are the complete equations. So back reaction is included. It's naturally incorporated into the result when you solve this equation.
Okay.
All right, thank you very much, everybody. There seems to be no more questions. Thank you very much, Paco.
Yes,
There's
one
another
question.
question. Okay, one last question. Kursit.
So CosmoLattice is important when the back reaction is dominant. Is it correct?
When what dominates?
When back reaction is start to dominate.
Yes.
Yes. Oh, thank you.
Okay, hopefully, I think we have covered all questions. Thank you very much, Paco, for the two lectures. Well, we will reconvene here in Europe. It'll be at 2 p.m. So there is now 1 hour and a quarter for lunch. In India, it will be 5:30 p.m. and in China, 8 p.m. if I got correctly my time shifts. Thank you all for coming, for the questions, etc. See you in a bit. Ciao, ciao. I'm gonna cut the connection now, okay? And then we will reopen at the time set.
Thank you.